All right, my friends, we've made it this far in the course. We've gotten a pretty good amount of practice with Solidity. We've seen a lot of Ethereum, and we've just touched a little bit on how to work React into the mix as well. In all this discussion, however, we've still really missed one very important point. We have not really discussed how we can build interesting, compelling applications using Ethereum that we cannot build with traditional technology like a traditional server and a traditional database. So in this video and many videos to follow, we're going to start working on a brand new project. And the goal of this project is to show you a rather interesting problem that can be solved quite elegantly by using blockchain technology. So that we're going to get a better sense of why we care about Ethereum. We're going to get a better sense of why we care about smart contracts at all. And hopefully it's going to give you a better idea of where to use these technologies in your own personal projects. So we're going to get started in this video. We're going to first discuss a startup that exists today. So this is a company that exists today. This company has been around for a couple of years now. Their startup seems to always run into one very repetitive problem. So let's talk about what the startup is. We'll then talk about what the problem is with the startup. And then we'll discuss how we can apply blockchain technology and Ethereum smart contracts in particular to solve this problem. So the startup we're going to be discussing is Kickstarter. Kickstarter. If you've never worked with Kickstarter before or you've never read about it, I will give you a very quick introduction right now. There's a tremendous number of resources online to tell you about what Kickstarter is and how it works. So again, I'll give you just a very quick overview. Let's imagine for a second that you are an inventor of sorts. So you're an inventor and you come up with some brand new product that you want to create. However, developing a product costs money, right? It costs money. You need money for employees, materials, manufacturing, whatever else. The idea of Kickstarter is to help you raise that money to build some initial prototype of your project. So you come to Kickstarter as a product owner and you create a new project or a campaign. On the right-hand side, you can see a list of some existing campaigns or projects that already exist on the platform. So you put together this project, you discuss about what you want to build. In this case, it's an oscilloscope, multimeter, and logger. And then you ask random people on the internet for some money. So people donate money to your campaign, and in exchange, at some point in the future, you will give that person some reward. So on the right-hand side over here, you can see some of the different pledge levels or some of the different donation levels that you can use to donate to the project. For example, if you donate 90 Australian dollars, then at some point in time you get a meter, a pouch, probe clips, battery, and a spare fuse. Boy, that sounds like a deal to me. I actually don't know, but you get the idea. The thing about Kickstarter is that the campaign creator only gets money if they meet some minimum funding goal. So this particular project stated that they wanted to collect at least $15,579. But at this point, they have obviously collected far in excess of that money. Once the campaign succeeds, Kickstarter takes all this donated money and sends it directly to the person who created this campaign. And it's then up to that campaign creator to go ahead and take that money, build the product, and then send that product to all the people who have donated to the campaign. So hey, that sounds like a great system, right? Some people need money to build their product. Maybe they can't raise or get financing for building that product. So they come to Kickstarter instead, do a little bit of marketing, and then walk away with the money they need to build their project. So where do things go wrong? What is the problem here? Well, the problem is that some people who create campaigns are a little bit malicious. It's totally up to the campaign creator to take the money that they get donated and then actually spend it to further their project and spend it to actually get a product that can be sent to their donators. But what happens in reality is that many of these projects end up failing. So they'll end up meeting their funding goal, they get a big old bucket of money, but then it turns out that they have no ability to actually efficiently manage a product, or creating a product, I should say, and then eventually they run out of money and they have to turn back to all of these backers and say, sorry, but we ran out of money and we can't give you your product. So essentially, all the backers lose their money completely, getting nothing in return. On the other hand are the people out there who are completely malicious, and the people who raise money for campaigns with absolutely no intent to ever make use of that money to build a product. As a matter of fact, if you go to Google and you do a search for Kickstarter scam, I mean, look at the autocomplete here. Kickstarter frauds, Kickstarter fails, Kickstarter failed to deliver. Here's 5 biggest Kickstarter failures. Scammers took the money and ran. And clearly this is a very repetitive problem that happens quite a bit on the platform. All right, so at this point, I have laid out a problem to you. Kickstarter exists, and we understand that, hey, sometimes when these people collect money, they don't actually deliver. Or maybe they don't deliver, maybe they just completely run off with all the money. So let's pause right here, and in the next video, we're going to discuss how we can use an Ethereum contract to at least somewhat solve the issue that Kickstarter is running into. So let's talk about how we're going to solve this problem in the next video. In the last video, we spoke about the startup Kickstarter, and we also discussed one of the big issues that they have today. In an ideal world, anyone starting up a project on Kickstarter will collect some amount of money from some contributors. All that money gets sent to the project manager, or essentially the idea person, the person who is going to make this thing happen. In an ideal world, that project manager would then take that money and maybe send it off to some vendors, right? They are not going to build, say, plastic casings themselves, so maybe this idea person is going to work with some outside vendors to get these basic parts put together, and then the idea person will then assemble those parts into the finished product. So this is just a for example. Let's just imagine that every Kickstarter campaign works with some number of external vendors. At the end of the day, they are collecting money for something, right? They got to be spending the money on something. So it's not unreasonable to say that all this collected money eventually gets sent out to some outside party by this idea person. Again, this is the ideal world. This is really what we want to have happen to see a successful Kickstarter campaign. However, the reality is a little bit different. So here is sometimes reality. Of course, there are very many successful Kickstarter campaigns, but sometimes this is what happens. We get all these contributors, they send money to the idea person, and then unfortunately, that money ends up in some private bank account, which is instead going to supply a vacation and a brand new BMW. So obviously not ideal. We don't want this to happen. So what's the common denominator between these two situations? Or maybe a better thing to say is, what's the difference between the two of them? Well, it appears that the big difference between these two situations is where this money goes. If we could somehow control this money being sent not to a private bank account, but instead to some vendor who's going to supply real project supplies that can be used to build some product, then it seems to me like we might have a little bit more successful product or campaign on our hands. That's going to be the exact goal of the contract that you and I are going to design. We are going to build a contract that is going to try to control where this idea person can send money to. So let's walk through this contract and discuss exactly how it's going to be put together. All right, so we're going to walk through a couple diagrams. We're going to start off with this very basic diagram. So at a very low level, we're going to say that contributors to a campaign are no longer going to be sending money directly to some manager or idea person. Instead, these contributors are going to send money to an Ethereum contract. So this contract is going to have some amount of code that regulates who can receive money from the campaign. We can think of this contract right here as representing the actual campaign. It's like a public display of all the expenses and fundings of the campaign. So how do we actually get money out of this thing then? How does the manager somehow work with the contract and say, okay, I need to actually make use of the money that's inside the contract now and use it to pay a vendor, as is what we really want to do over here, right? We want to pay vendors because that's probably going to lead us to a successful campaign. So in order for a manager to actually spend money, we're going to say that they have to create something called a spending request. So in the contract, they're going to call a function that creates a spending request. A spending request is going to attempt to withdraw money from the contract and send it to some specific external address. And in this case, we're going to say that this external address is some vendor. So maybe it's someone who's going to make a battery casing for us, or an LCD display, or some sensor clips. Essentially, someone who is going to help us further the campaign along and make sure that we actually are trying to build a product and not just run away with all of our money. So how does a spending request actually do anything though? Well, here's the twist. Here's the fun part. So here's where the real Ethereum stuff starts to come into play. We're going to say that the manager has the responsibility to create a spending request to pay an outside vendor, right? That makes sense. But here is the interesting part. We're going to say that all of the people who contributed to a campaign have to vote on every spending request. So manager says, hey, I need like $100,000 to buy some battery casings. They're going to create a spending request inside the contract. It will then be up to all of the contributors to call a function on the contract to approve that spending request. So each of these contributors right here have to call a function to approve the spending request. If enough people approve the request, then the funds automatically get sent to this outside vendor, and in theory, that vendor will now deliver some supplies to complete the campaign. However, if too many people vote no, then that is an indication that this is a bad request and that the manager is mismanaging the campaign in some fashion, and they really need to get their act together. Otherwise, these contributors are not going to approve the spending request, and no money will be able to be spent out of the campaign. So obviously this might have a couple of holes in it. For example, we're kind of relying on the fact that all these contributors are either going to vote yes or no. We're also making the assumption that the manager is not going to try to trick these contributors into sending this money to a fraudulent address or a fraudulent vendor. Yeah, there are issues like that. However, at the end of the day, this approach right here goes a lot farther to producing successful campaigns in the real world than the current Kickstarter system. The current Kickstarter system says, okay, manager, here's your money, go and do the right thing. And there's no outside control whatsoever from these contributors. They send their money into Kickstarter and that's pretty much it. They wave goodbye and they can do not a single darn thing to influence the campaign whatsoever or make sure that it's being ran responsibly. So with this type of approach, by using an Ethereum contract, at least these contributors have an idea of where their money is being sent to, and they have the ability to review these spending requests before the money gets spent. So again, maybe it's not the perfect solution in the world, but it at least gives a lot more power to these contributors than they would otherwise have. All right, so that's pretty much it. That is our solution. That's how we might use an Ethereum contract to solve this problem that Kickstarter has. Now you might be thinking, okay, Stephen, that's great. Sounds like a solution, whatever. Well, hey, it's not enough to just talk about this. We're gonna build this, right? So in case it's not clear, we are gonna build this contract. You and me, we're gonna build this thing. It's gonna have all the functionality that I just discussed, and then we're gonna put together a fantastic looking front-end application to sit in front of all this. And at the end of the day, we are gonna have a system that very closely approximates how Kickstarter behaves. So this is going to be just an exceptionally exciting project. I can't tell you how excited I am to get started on it. So let's pause right now. We're going to come back in the next video and we're going to start writing some code to build this Kickstarter clone. So I'll see you in a minute. We're going to approach the development of our crowdfunding contract in the same exact fashion as how we approached the lottery contract. So we're going to first talk about the design of the contract. We'll then write out the contract in the Remix editor, and then we'll develop a React front end around that. So with that in mind, in this video, we're going to talk about the design of our crowdfunding or our campaign contract. I'm going to be using the term campaign and crowdfunding quite interchangeably throughout this entire series of videos. Whenever I say campaign, I'm talking about a project that we are trying to create to raise some money to build some product. So I'm going to say campaign, I'll say crowdfund, all meaning the same thing. In this diagram, I've listed out a bunch of the different variables and functions that I think that our contract is going to eventually need. This is going to be a first take on some of our different variables and functions. And what I mean by first take is that we might end up changing this design a little bit as we work through it. In particular, I'm going to tell you right now that the design of this approvers variable and this approve request function right here are going to change a little bit, because as soon as we start working on those, we're going to realize that they're going to run into a little issue. I know it's kind of annoying in a tutorial where we do things the wrong way, and then I say at the very end, oh yeah, well, we did things the wrong way here, and here's how you should do that. So I'm telling you right now that we're going to come back to this approvers variable after we implement it. We're going to point out one really big issue, and then we're going to refactor it to take a slightly different approach. The reason we're doing this, the reason I'm going to show you a bad way of doing things, is that this is something that I know you're going to run into on your own projects. So I want you to experience the problem that we're going to run into in a very natural fashion. All right, so with that in mind, let's talk about some of the different variables. Now, a lot of these variables will look very similar to the variables that we used inside of our lottery contract. And of course, we did that lottery contract before this one very much on purpose. So we're going to be borrowing a lot of code and a lot of ideas from the lottery contract, because it is vaguely kind of a similar setup where we have people entering into some contract and they then belong to it or have some type of relationship to it. The first variable right here is going to look very familiar, the manager variable. This is going to store the address of the person who is managing this campaign. You can imagine this is the kind of idea person, or the manager over here. It's the owner of the contract. It's the person who's trying to raise money to build some sort of product. This person is going to have an elevated status above all other people, and they're going to have access to methods that other people will not have access to, just like our lottery contract had that pick winner function. It will be of type address, and again, it's basically going to be the same thing as what we did on the lottery contract. The next variable is going to look very similar as well. This variable is going to be called minimum contribution. So the thought here is that in a real Kickstarter project, there are different tiers that you can donate to. A tier is speaking about the amount of money that you are contributing to the project. And if you donate more money, you qualify for a higher tier. If you donate only, say, $1, then you really don't get that much. But if you donate $90, well, then in this case, you get the actual product. So that's the idea behind this minimum contribution variable. This is going to be the minimum amount of money required to donate to the campaign to be marked as a true contributor. If you want to, you can certainly donate less money, but we're going to say that you have to donate at least minimum contribution in order to be considered a contributor to the campaign. Next is our approvers array. So this will be a list of the addresses for everyone who has donated money meeting that minimum contribution. We're calling this array right here approvers because this is going to be the people who approve requests. Technically, we can think of these as campaign contributors or people who have donated money, but as far as the contract goes, at the end of the day, they are really functioning as an approver for requests, and that's why we're going to call them an approver. If we look back at this diagram right here, the list of people down here, yeah, this would be our approvers. This is an array of addresses, and just like before on the lottery contract, we will enter in the address of everyone who enters in. Now, like I said at the start of this video, we are going to run into a big issue around this approvers array. So it's going to be a little thing that we're going to have to figure out, and of course we'll go into great detail. Again, we are going to end up refactoring this variable right here to be a slightly different type to store our addresses, but we'll get to that in due time. Next is the requests array. So this is what's going to store a list of requests that the manager has created. Remember, this is really the backbone of the entire contract. It's what enforces some amount of security. Anytime the manager wants to spend some money, they have to create a spending request. And the spending request is going to say, all right, I want to send maybe 10 Ether over to this vendor, and this vendor is going to do some work for us to further along the campaign. The manager is going to probably want to make many different spending requests because they might want to send many different people some amount of money. So of course, we want to make sure that we have the ability to store a list of spending requests. Now the type of this variable, you'll notice that I marked it here as request and then the square braces. So this is going to be an array that contains variables of type request. And we'll go into good detail to explain exactly what that means. All right, now just a quick overview on some of these functions because I think you'll very quickly understand what they do. First off, we have the constructor function, which of course is named as campaign. This is going to set the minimum contribution and the owner on the contract when it's first created. We're going to have a contribute function. This is what very common people who want to donate to the campaign are going to call in order to donate some amount of money. So if you want to become an approver, you're going to call the contribute function and send in some money. And as long as that money meets the minimum contribution, then you will be marked as a contributor. The contribute function can be thought of as being very similar to the enter function that we put together a little bit ago on our lottery contract. Next up is create request. This is the function that a manager can call to create a spending request. And again, we'll go into good detail on discussing exactly what a request is. After a request has been created, contributors can then call a function named approve request to approve an individual spending request. So again, this would be very much like this case right here, where the manager has created a spending request and all the contributors have to essentially vote on a given request. Now, after a request has been approved, after it's gotten an appropriate number of votes, we're not going to immediately disperse the money. In other words, we're not going to immediately take the spending request right here and send the money inside of it to the vendor. So we're not going to just say, okay, well, enough people have voted yes, take the money and send off to the vendor. In the real world, the manager might want to create a spending request and then make sure that it can get approved before they actually finalize terms with a given vendor. So just because everyone said, yeah, that's fine, go ahead and spend the money, maybe the manager is not quite ready to pull the trigger, so to speak, and send this money off to the vendor. So to accommodate for that type of situation, we're going to have a finalize request method. Finalize request will allow a manager to look at a finished request or a request that has gotten enough approvals. And once they call a finalize request, it will then take that thing and actually disperse the money or actually send it out to the particular vendor. So in short, the entire purpose of finalize request right here is to give the manager a little bit more flexibility on when the vendor actually gets paid. That's all. All right, so that's an overview of our campaign contract. I think in general, it's not going to be that bad. I think that we're going to get through it a-okay. The one thing to be aware of, again, is that this approvers variable right here is going to end up changing a little bit. And you'll notice I also put some exclamations next to approve request down here. That's because when we change approvers, yeah, we're going to make a little change to approve request as well. All right, so with all that in mind, let's continue in the next video, and we're going to start working on this contract inside of the Remix editor. So I'll see you in just a minute. In the last video, we spoke about the overall design of our campaign contract. We're now going to move over to the Remix editor and start writing some code to implement the contract. Again, once we finish up the implementation, we'll then introduce the React side of our project and put together a really nice looking front end for this thing. So I'm going to flip on over to my Remix editor. If you've already closed it, remember you can access it at remix.ethereum.org. Once inside of here, you might see that all of our code from the lottery contract is still on the screen. So you can highlight that entire contract and delete the entire thing. And so we're left with essentially an empty file, except for the remaining pragma mark at the very top. Inside of here, we'll immediately define the new contract. I'm going to call this thing campaign because that's really what it is. It's a crowdfunding campaign. We could also call it something like, say, crowdfund. We could call it project. You know, at the end of the day, it doesn't really matter, but I think campaign makes a lot of sense. The first function and the first variable that we're going to define in this thing will be around handling the manager. So remember, the manager is going to be the address of the person who created and is managing this campaign. And we're going to set its value inside of the constructor function. So back inside the contract, we'll tell our contract, hey, you're going to have a variable called address. We're going to make it public, and its name is going to be manager. We've spoken about the difference between public and private many times. This is another case where, hey, I really have no problem if people want to find out what the address of our manager is. That's totally okay for me. In fact, for a crowdfunding campaign, we probably want this information to be public. We want people to have very easy access to figure out exactly who the manager is. because that just instills a little bit more confidence if you understand who is working with the money for a given campaign. Right underneath that, we'll then define our constructor function. So we'll say function campaign. I'll mark it as public. And then inside of here, we'll take the address of the manager or the person who's creating the contract and assign it to the manager variable. So we can say manager equals message.sender. We've used this message global variable before. Remember, we don't have to define it or do anything. It's just a variable that is always available to us. And then we're going to refer to the sender property on it. The sender property describes exactly who is attempting to create the contract. Now we did this pretty quickly, so hey, while we're here, let's also take care of that minimum contribution variable as well. Minimum contribution is going to be an unsigned int. It's going to reflect the minimum amount of money required for a contributor. In the past, we had said on our lottery contract that it was always a fixed amount of 0.01 ether. So this time around, we are acknowledging that people might have different minimum funding requirements, and we're going to allow them to set this value on the fly. We'll take this as an argument into the constructor function. We've done this once already back on our inbox project much earlier in the course. So we're going to say that whenever someone creates a new instance of a campaign, they should be passing in a uint, and we'll call this thing minimum. And then inside of the function body, we'll take minimum contribution, and that will be the minimum variable argument. And then notice that the editor is complaining a little bit because we have not yet initialized this variable. So back up right underneath our address, we'll say that we're going to have a uint that is also public, and it's called minimum contribution, like so. All right, so nothing too crazy yet. We've defined our two variables and a constructor function. Let's pause here, and then we'll continue the next section and start working on some more of our variables and functions. In the last video, we put together our constructor function and initialized the manager and minimum contribution variables. We're now going to move immediately onto our approvers variable and also create the contribute function. So let's get started. Back inside of Remix, we'll first initialize the approvers variable as an array of addresses. So we'll say address, the square brackets, we'll mark it as public, and then we'll give it a name of approvers. Do triple check and make sure that you've got address with two D's right here. Again, very easy typo to make. Next, we'll put together the contribute function. Remember, this is going to be called whenever someone wants to send some money to our contract. Now that's kind of a key word right there. Send some money to our contract. Anytime someone is going to send some money, we need to mark the corresponding function as being payable. Don't forget. So we'll say function contribute. We'll mark it as public, and we're going to also mark it as being a payable function. So payable right here is what makes this function able to receive some amount of money. When someone calls this function, we do need to make sure that they pass in the appropriate amount of money, or at least an amount of money greater than the minimum contribution. So at the top of the function, we'll add in a require statement to look at the amount of money that this user is sending and make sure that it is greater than the minimum contribution. So we'll say require message.value greater than minimum contribution, like so. We've used the message variable here quite a bit. Remember, it's a global variable. One of its properties is value. Message.value is the amount in way that someone has sent along with the transaction that is targeting this function. If this person does not send in greater than the minimum contribution, then the require statement right here will throw an error and immediately exit the function. All right, so if they get past that line of code, we can then take this person and add them on to our approvers list. So right underneath this, we can say approvers.push, and then we need to get the address of the person who is sending in this transaction. Again, that's coming from our global variable message, and it will be message.sender, like so. All right, so that's a pretty easy place to get started. We've already got our constructor function and our contribute function. Now, as you well know, I've mentioned several times that this approvers variable is going to eventually run into an issue. So I think that right now, we'll take a break. We're going to come back to the next video and test our contract out. After we test it out, we'll then start to talk about some issues that might arise because we are using an array for this variable right here. So let's start that in the next video. We've put together a little bit of code for our campaign contract. And I think that before we go any further, we should do a quick test inside of Remix to make sure that the code we have is behaving the way we expect. I'm going to pull open the right-hand nav over here. I'm going to make sure that I'm on my Run tab and that I have an environment of JavaScript VM selected. I'll then scroll down a little bit and find the box that I can use to create a new instance of the campaign contract. Remember that we've said that there needs to be some minimum contribution provided in order to contribute to the campaign. We need to provide that as an argument to the constructor function. I'm going to say that you have to spend at least 100 Wei to get added as a contributor to this project. Remember that this is a value in Wei right here, it's not in Ether. So we'll click Create, and I should see my new instance of the campaign contract appear down here. If I click on Minimum Contribution, I should see 100 Wei. If I click on Manager, I should see my address, and at present we do not yet have any approvers. So this approvers array should be entirely empty. Let's now try contributing to our contract and then making sure that we can retrieve this new contributor from the approvers array. So I'll scroll up a little bit. I'll find value right here. I'm going to make sure I put in a value greater than 100 Wei. So I'll just do 101. Why not? All right, now I'm going to make sure that I have my console open so I can watch this thing and see if an error occurs when I attempt to contribute to the campaign. So I'll contribute, and yep, everything looks okay. Now I can attempt to get the first index out of the approvers array by entering a 0 right here, and that returns to me my address. So I am definitely marked as being an approver. All right, I know that this contract so far is not much different from the lottery contract, but after this point, we're going to start making some big changes to this thing that is going to make it very dramatically change in behavior from how the lottery worked. So let's start working on some of those more interesting things in the next video. We've now got some basic functionality for our campaign contract put together, and we just tested it inside of Remix to make sure that it's at least somewhat going down the right path so far. The next thing we're going to work on is to implement the idea of a spending request. We have the ability to recruit people or to accept contributions, but we do not yet have the ability to send any money out. So we can't use any of the money we're receiving yet. That's the purpose of the request. Remember, a manager is going to call the createRequest function, and that should create a new spending request. We had said that this request variable was going to be an array that holds a list of individual requests. I want to first talk about what this request thing is going to be in terms of its actual type or data structure. For that, we're going to need a quick refresher on something that we spoke about a couple videos ago. So here's a chart of all the different reference types that are available to us inside of Solidity. We've made extensive use of dynamic arrays so far. We had said that there were also fixed arrays, mappings, and structs. Mappings and structs were vaguely similar in that they were both collections of key value pairs. A mapping was all about storing records or storing some very similar records, whereas the purpose of a struct was to model some given individual object or something. And a good example of that was creating a struct that represents a car. And in this case, maybe a car has a make, a model, and a value assigned to it. So we're going to create a new struct inside of our contract that is going to be called a request. The struct is going to have a couple of different fields that describe the purpose of the request. So let's take a look at another chart that's going to help us understand this request thing that we're going to make. All right, so here's our request struct. These are names of the different fields that we're going to place on the struct. Each field has its own individual type, and then of course every field has its own purpose. We're going to create this new type called struct, or excuse me, this new type called request, And then anytime a manager wants to create a new request, they're going to essentially be creating a new instance of this struct. So you can think of the struct as kind of being like a class of sorts. And if we ever want to make use of it, we have to first create an instance of it. And we'll see some very good examples of that in due time. Let's first talk about the different fields that are on here and why we are using each of them. The first one will be a description field. This is going to be pretty self-descriptive, pun I guess. Anyways, the point of it is to explain to contributors or approvers why the request is being made. So a manager needs to somehow justify any money that is being spent or withdrawn from the contract. A manager might give a request a description of something like, I need to pay this vendor to get some battery casings, or I need to pay this vendor to pay for shipping, or I need to pay this vendor to get some paint, whatever it is. This is going to be the area that a vendor can, or excuse me, a manager can use to justify the expense to all the contributors. Next up is the value. This will be an unsigned int, and it's going to represent the amount of money that the manager wants to send over to this third party or this vendor. So I think this one is also pretty clear. This is how much money we want to withdraw from the contract and have be sent to someone else to pay for something. The next field is also pretty self-evident. It's going to be the recipient. This is going to be essentially the address of the vendor. This is the person who is going to receive some amount of money. In theory, all of our contributors or the approvers can look at this recipient property, look at the address, and have some reasonable belief of, okay, this address I know belongs to this big electronics manufacturer. So if the manager just made a request to send that address some money, chances are they are in fact buying battery casings or LED screens or whatever it is. So this is the person who's going to eventually receive the money. The next one is a little bit more interesting. So this is going to be a field that we're going to call complete. The interesting thing about this request is that we don't really have a great way of knowing whether or not the request has been executed. We don't know whether or not this request has been taken, paid up, and had the money sent out. So we're going to add a simple Boolean to the request that says whether or not the request has been processed or essentially been voted on, approved, and then had the money sent out. Of course, we're going to want to make sure that if the request has already been marked as complete, it should not be able to be sent out or processed again. So once a request is marked as complete, that's it. You cannot send any more money through this request again. The one thing you'll notice that I have left off on this request struct is some type of voting mechanism. So we haven't really discussed how our contributors are going to vote on a request, because remember, that's the entire point of this whole exercise. We want to make sure that whenever a manager creates a spending request, all of our contributors have the ability to vote on it and either approve it or disapprove it. So that's something that we have not yet incorporated into this request struct. We're going to come back to this topic in a video or two because it definitely requires its own separate explanation. For now, let's flip back over to Remix and we're going to create this new type of request. All right, so we'll go back over to Remix. We're going to define the struct at the very top of our campaign. So even above the variables here. Up here, we're going to place the struct keyword, and then after it, I'll place the name of the struct that we are creating. And in this case, it's going to be request, like so. Then inside of here, we'll list out all the different fields that we want this request to have, or we want this struct to have, and we will also list out the variable's type. So we'll say string, and then description, and then finally a semicolon after that. This defines a new field on the struct called description, and as you might guess, it sets its type to be a string. We can repeat the same process for all the other fields that we want to add. And then do take note, we're placing a semicolon after each individual field. So this is distinctly different from JavaScript objects or any other type of object thing you're used to, where usually we separate them by commas. So no commas here, we're doing a semicolon. So next on our list, let's see what we had next. We had, value, recipient, and complete. So value is going to be an unsigned int. The recipient will be an address. And then complete is going to be a Boolean, which is simply bool, so true or false. complete, like so. Now, one thing I want to be really clear on, because you'll see this request struct that we're creating right here is placed right next to all these other variables. These variables right here instantly created a local or instance variable tied to the contract. So when we said, hey, this thing's going to have an address called manager, then hey, we suddenly got this variable that we could get access to from all of our functions anywhere in the contract. And that's how all these different variables that we've declared so far behave. However, a struct that we define right here is a struct definition. So this does not create an instance of a request. We cannot now go into some function. We cannot do this. We cannot now say like, oh, request is going to be ASDF or whatever it might be. When we place a struct definition, we are introducing a brand new type into our contract in the same way that we have types of address, uint, or array of address. So again, this is a type. It's a definition. It is not an instance of a variable. When we eventually want to make a request, we will create a new variable and we will specify that its type is request. So in closing, just one more time, just to be really clear, this does not limit us to having only one request at a time. We can have as many requests as we want because this is just defining the idea of a request. All right, I think I've hammered that in enough, so let's take a break. We'll come back in the next video and we're going to start implementing some of the logic to allow a manager to actually create a request. So we'll take care of that in the next video. In the last video, we introduced the idea of a request struct into our contract. We're now going to start working on the create request function right here, and we're also going to create our requests array. Remember, just like I said at the end of the last video, this does not create an instance of a struct. It just creates the idea of one. It creates the type inside of our campaign. So to actually create a request and store it inside of our contract, we're going to make an array that specifically holds variables of type request. So let's take care of that first. Back inside of our contract, next to all the other variables that we have defined so far, we're going to make a new array and specify its type as being request. So we're going to do that in a very similar fashion to how we define the array of addresses right here. We'll say request with a capital R, square braces or square brackets, then public, and requests, like so. Notice that we're using a capital R here because we used our capital R to define the struct. By convention, we usually use a capital R whenever we are defining a struct, which is dissimilar to how we usually do all of our type definitions or type annotations. This variable of type array of request is given the name requests. So now anywhere inside of our contract, we could make reference to the requests array. So I could say request.push and I could push in a new request. I could say give me the first request in there by using the square bracket with index of 0. So in general, it behaves just like an array, but rather than an array of addresses or an array of numbers or whatever else, we are working with an array of requests. Cool, so that looks good. Let's now move on. We're going to start working on our create request function. Now this is going to be called by our manager to create a new spending request. In other words, create a new variable of type request and then add it into our requests array. One thing I want to point out about this function is that we probably only want a manager to be able to call this thing. We don't really want a contributor to be able to call it, and we certainly don't want some random person to call it. Only the manager should be able to create a request. Otherwise, some malicious people might come along and create a bunch of fraudulent requests that tried to pay some bad person all the money inside the contract. In other words, we need to make sure that we lock down or restrict access to the create request function. And that definitely sounds very similar, very familiar. If you remember back to our lottery contract, we had put together the pick winner function. And for that, we wrote a modifier, a function modifier, to lock down access to it. So I think that before we even start working on create request right here, we might need to create another function modifier to lock down access to the create request function. When we put together that function modifier on the lottery contract, we only used it in one place. However, I very quickly would get the feeling that we would want to lock down not only create request in this case, but probably also finalize request as well. So in this case, we'll be able to use this modifier probably in more than one location, which would be really nice. All right, so let's do this modifier. In practice, it's going to look basically identical to the one we already put together. Traditionally, we place all of our modifiers directly above the constructor function. We didn't really follow that rule over on our lottery contract, but we are this time around. So right above the constructor function, I'm going to give myself a little bit of space, and then we will create a new modifier called restricted. The code inside this thing is going to be absolutely identical to the restricted modifier that we put together already. So we are going to require that whoever is calling a given function, so message.sender, has the exact same address as whoever had created this contract, which is going to be our manager variable. So we'll require that message.sender is equal to the manager variable. Then remember how a modifier works. The modifier we can kind of imagine is going to take an entire other function and like paste it into the body of this thing. And we mark where we want all that code to be kind of virtually pasted by placing our underscore. So right after the require statement, we'll place underscore semicolon like so. This introduces a modifier called restricted. So now we can take restricted and add it to any given function inside of our contract. So we could add it onto contribute, but that definitely does not make sense. We want anyone to be able to call contribute. We really only want to lock down or restrict access to the create request and finalize request functions. All right, so now that we got the modifier put together, let's take a pause here. We'll come back in the next video and we're going to start working on create request. So quick pause and I'll see you in just a minute. Now that we've got our restricted modifier put together, we can start to create the create request function. I'm going to flip back over to my Remix editor and we'll add this new function towards the bottom. I'm also going to give myself a little bit of space here just so you can see everything more easily on the screen. All right, so right underneath contribute, I'll add on a new function called create request. This thing is definitely going to take some number of arguments, but we'll come back to those in just a second. First, let's make sure that we annotate this function properly. We want the function to be public because it should be able to be called from an external account. We do want to make sure, however, that we also lock the function down by using the restricted modifier. So after public, we'll say restricted, like so. And then we'll open up our curly braces. All right, so now let's focus on the argument list right here. Remember that the purpose of this thing, the purpose of the create request function, is to create a new struct of type request and then add it to the requests array. And we had created those 2 videos ago. So here's our struct of type request, and we've got our array of requests right here. Whenever we create a new request, we definitely want the description, the amount of money, and the recipient to be provided by the manager. These are values right here that you and I can't just guess on the fly. It's really the manager who has to specify the purpose of the request, the amount of money that they want to send, and who they want to send it to. So I think that we need to have all 3 of these right here come in as arguments to the create request function. So let's add those on right now. Down inside of create request, we'll first take in string description. We'll do a uint for value, and then an address for recipient, like so. Now you might notice that this line of code right here is getting very long. If you want to, you can absolutely put a new line right before public, if I can click on this thing, and then kind of do up our indentation to be like so. So this is 100% equivalent. You might also sometimes see like this type of syntax right here. And the entire purpose of this is just to allow us to read one entire line. So you'll sometimes see this in a lot of literature, blog posts, or what have you. Now personally, I don't quite care for that so much, even though it's really going over the character limit here. So I'm going to keep everything on one line. It's really up to you how you want to do it, but doing the indentation would be a little bit more consistent with style practices in the community. But again, this is kind of a pet peeve of mine. I am totally okay having the line run long. All right, so now inside of here, we're going to take these 3 arguments. Oh, Boy, that scrolling is really crazy. I hope it's not going to keep doing that, otherwise I will have to do the indentation. Anyways, we've got the list of arguments right here, so we now need to use these to create a new request and then add that request to the requests array. So let's write out the code that's first going to create our new request. This is going to be a little bit crazy, and we're going to see the word request many, many times, but I'll make sure it's really clear what the purpose of each word is. We're going to first say capital R request, then new request equals capital R request. We'll then open up a set of parentheses, a set of curly braces. We'll put a new line in, and I'll make sure I get a semicolon on that thing. Then inside of here, we're going to place a collection of key value pairs that specify the description, the value, the recipient, and so on. So I'll say description is going to be coming from the argument description. So this right here is the field that we care about, and we're going to set its value to be the argument description. Then we have value, again coming from the value argument. And we have recipient coming from the recipient argument. And you'll see a little error here. Let's see what we got. Wrong argument call. So the last thing, oh, we left one off, that's why. We also had that complete flag. So complete right here, we need to make sure that we specify that as well. So finally, complete, and that needs to be defaulted to be false because of course when we first create this thing, it is not ready to be completed. Now we still have a little error message here. Let's see what's going on. Okay, so this is something, you'll see a little error message right here. I wasn't expecting to see that error message, but it's about a topic that we're going to discuss in the next video. So we can just kind of ignore this error message for right now because we are going to come back in the next video and talk about why you see it. So the last thing I want to do for right now is take this new request and add it into our requests array. So right underneath it, I'll say requests.push new request, like so. All right, so we just wrote a pretty good amount of code and we have an outstanding error and we've got the word request all over the place here. So let's take a quick pause right now. We're going to come back to the next video and really break down this entire chunk of code in great detail. In the last video, we wrote a pretty good amount of code and we still have a pending error message on the screen. I want to first start off by talking about what we did here on line 33 when we created a new struct. So let's break down this line and make sure that we really understand what's going on with it. All right, so here we go. At the very left-hand side, we have the word request with a capital R. This is a reference to the struct that we had defined at the top of our contract. The word request right here tells Solidity that we are about to create a new variable that is going to contain a value of type request. Immediately after that, we create the new variable. So this is the name of the variable that we created, and its name is new request. Notice that this doesn't have to have the word request in it at all. It obeys all the same rules as normal variables. So it could have just as easily been like orange or elephant or ABCD, whatever we want it to be. But definitely a variable name of new request makes a lot of sense right here. So taken together, on the left-hand side of the equals, these two words mean I want to create a new variable called new request, and that variable is going to hold a value of type request. Now everything on the right-hand side of the equals is much more concerned with actually creating an instance of a struct. So the left-hand side is a little bit more about storing that value. The right-hand side is about actually creating it. So to create a new instance of a struct, we place the name of the struct, a set of parentheses, a set of curly braces, and then inside there we iterate all over the different fields that we want to initialize this request with. In the last video, when we were listing out all the different fields, you saw me pause for a little second right before we define the complete field. So if we take that back out, so let's delete that for a second, you're going to see that we get another error message here added to the list of the two that we already had. And let's see, the second one, I can't move my cursor, but the second one down, the one that says type error, it says wrong argument count for function call, 3 arguments given, and then the rest of that line probably says something like but expected 4. So whenever we create a new request, we have to place every different property that the request is going to be initialized with. So at the very top, we had said that the request has a description, value, recipient, and complete, so it expects 4 different fields to be defined. But if we only do description, value, and recipient, we're only providing 3 of those fields. So that's why I hesitated there for a second, and yes, we definitely do need to specify the Boolean complete like so. And so once we add on all 4 fields, that error message went away. And we only have the other 2, and again, we'll discuss those 2 in just a moment. Now there's something else I want to mention about declaring structs as we did right here. So specifically declaring the struct on the right-hand side. We used a key value pair approach to defining the struct. However, there is another way of defining a struct that does not involve all the keys listed out. So we don't have to always list out description, value, recipient, and complete. So this is an alternative syntax. I want you to be aware that you can use this alternative syntax, and you will sometimes see it used in a lot of blog posts and documentation. However, I very, very highly recommend you do not use this alternative syntax. Okay, so I'm going to show it to you so you know what it is. I highly recommend you not use it. So the alternative syntax would be to say simply request, then description, value, recipient, and false. All right, so what do we just do here? So this little segment right here could be used as a replacement for this block right here, specifically everything on the right-hand side. So both the highlighted portion right here and this highlighted portion right here both declare a new value of type request, which is a struct. The difference is that right here we're defining all the different fields and the respective values. Down here we provide only the values. So the word description is not the field name. Description right here is coming from the argument list. And then we have value that comes from the, I'm so sorry about that scrolling. I know it's really annoying. It is the code editor. I won't click on that line anymore. So we've also got value, which is coming from the argument list. We've got recipient, which is from the argument list. And then clearly this very last argument right here makes it very obvious that these are all values because we pass in false, which is supposed to represent complete. So again, these 2 syntaxes are completely equivalent. The second one right here, however, works in a very tricky way. So you'll notice that I very clearly did not specify which value belongs to which field, right? Like I say nothing in here that says, oh yeah, this value false right here is supposed to be assigned to the complete field. So that alternative syntax is all based on having a consistent order of fields. So you see up here where I define the struct, we said description, value, recipient, and then complete. So when we use this alternative syntax, Solidity assumes that the first argument will be used for the first field defined in the struct. The second will be for the second value or the second field defined in the struct, recipient for the third, and false for the fourth. So it's all about the order in which we list out these fields right here. And when I say that, maybe you will very quickly get a sense of why I very highly recommend not using that syntax. Well, here's why. I'll give you a very obvious example. If I reorder the fields inside this definition right here, like let's say if I move bool up to the top, what's going to happen? Well, now everything shifts by 1. The first value that I pass into the request with that alternative syntax should be a Boolean. So if we now go down to the bottom, you're going to see an error message. And the error message is talking about the types of all these different fields that we are passing into the request struct right here that we're trying to create. So it's saying, hey, you're trying to pass in a string that is supposed to be a Boolean. You're trying to pass in a value that is trying to be a string, and so on. So it basically reorders the order of arguments in there. I could get that error message to go away by moving false up to be first like so, and now you see that error goes away. So I feel like, you can very quickly understand how someone might decide to do a little bit of a refactor to your code, and they'll say, oh, you know what, I want to see all my Booleans defined up top rather than at the bottom. That's a really easy refactor for someone to do, and if they did that, they would then very suddenly break a bunch of your code. Now in this case, it wasn't that bad because you and I clearly saw that we got some error messages. However, imagine for a second that the entire struct had all the same types. Like maybe these were all of type bool. And then maybe when I create my new request right here, I had a very specific order. I wanted to say specifically true, 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 and then false. Well, if I now flip the order of these, let's do it right now, just to give you a very clear example. If I now moved recipient, or excuse me, if I move complete down to the bottom, like so, I'm not going to get an error message. So I do not get an error message because there's no issues with the types that are being assigned here. However, you can see that false will now be assigned to a different property than it was assigned to before. So I know this is probably getting a little bit confusing, but please just take my word for it. I really encourage you to avoid using this syntax because it's just way too easy to run into a small issue. All right, so I'm going to clean this up, and then I'm going to go back up to the top and reorder the fields inside of my struct. So back up here, we have description of string. I should have just hit undo, but oh well, here we are. So I got a uint, an address, a bool, and that's it. So as you might imagine, when we use this key value approach right here, we can jumble the order all we want. So I can change that order and I get no additional error messages or anything like that. So now description is third and description is fourth. We get no, well now I get an error because I've got the dangling comma, but you get the idea. So I can't say it enough, highly recommend you use this key value syntax that you see right here, as opposed to that alternative, more shorthand way of defining a struct. But that's just my take. All right, so anyways, back to the struct itself. We define the struct, we assign it to new request, and then we push that into our array that holds a list of all of our different structs. So I think that probably makes sense at this point. However, we still have the error message right here, and it appears that the error is complaining about storage and something about memory. So let's take a pause right here. We're going to come back in the next video and talk about what this error message is complaining about. So I'll see you in just a minute. I think that we now have a much better idea of what's going on inside the create request function. However, we still have an error message on line 33 or so, and the error messages appear to be mentioning something about storage and something about memory. So in this video, we're going to get a much better sense of what this error message is talking about. Before we dive into any of the specifics here, I do want to make a very quick side comment. I'm going to say that in this video, you might be thinking I'm going way too in-depth on some of these topics we're going to be discussing, and it might seem like this is a video that is a little bit out of place. However, the error message that you're seeing right now is one that you will see on your own personal projects. And all the documentation out there that explains this error message is really very not helpful. So I want to spend a good amount of time talking about this error message because when you come into contact with it on your own, it's going to be a pain to troubleshoot, and I can just about guarantee that. All right, so here's why this error message is so troublesome. This is why it's so confusing. The error messages themselves, each of them, one says storage and the other says memory. Storage and memory are two terms that are used across two different topics in the world of Solidity. Okay, that's the first thing to understand. When we say storage and when we say memory, they are both referring to two separate topics. So let's figure out what those two topics are. So again, when we see these terms right here, sometimes storage and memory are referencing where our contract stores data, like where it stores arrays and integers and strings and whatever else. And then sometimes storage and memory are referencing how Solidity variables actually store values inside of our contract. Now these are two topics that are very closely related, but nonetheless, they're two different ways of talking about storage and memory. So you're going to see storage and memory, and sometimes it'll be in documentation that's talking about where our contract stores data. However, in other times, you'll see storage and memory, and it will be talking about how Solidity works with variables. So that's kind of challenging aspect number one. We're going to first speak about this first case right here, where we talk about storage and memory, and it's in reference to how our contract stores data. So we're going to first cover that because it's a little bit easier to understand, and then we'll come back and talk about this variable thing over here. And just so you know, when we are dealing with that error message that we saw a little bit ago, it's all having to do with this second case over here. However, all the documentation and blog posts and Stack Overflow posts you're going to find online are all talking about this first one. And this is the easier one. So all the documentation tells you about this easy thing. None of the documentation really makes this more challenging thing that is related to the error message that we see very clear. All right, so I think that's enough preamble. Let's just get right into it. We're going to talk about storage and memory as related to where our contract stores data. Okay, so this is all about where our contract holds data. On the one hand, we have one bucket of location, or one bucket where we can store a bunch of data, and we refer to it as storage. Storage is used to hold data between function calls. An example of storage is all of the different variables that we have initialized at the very top of our contract right here. These are all variables or pieces of data that are held in our contract's storage. Storage is available between function calls. So if we call one function on our contract and we modify one piece of data, that piece of data is available on our next follow-up function call. So in general, this idea of storage is something that we've been already working with a tremendous amount throughout this entire course. A good way to imagine storage as being just like your computer's hard drive. If you write some file, like let's say a text file, to your computer's hard drive, and then you turn off your computer and then turn it back on, that data, that text file, is still going to be there. It doesn't matter that you turned off your computer. You wrote it to some long-term storage mechanism, your computer's hard drive. So that's how we want to be thinking of storage. On the other hand is memory. Memory can be thought of as a very temporary place to store data. And as you see over here on the right, a good way of thinking of it is just like your computer's RAM. If you store some data in your computer's RAM and then turn off your computer entirely, like you cut power to it, no electricity whatsoever, and then turn it back on, any data that had existed in RAM will then be completely emptied out. It's totally gone. So again, storage is all about preserving data. Memory is about very temporary data. We technically have seen an instance of memory data once already. So I can show you that inside of our contract right here. We have our variables up here that are storage data, but if we scroll down to, say, our constructor function right here, you'll see an example of memory data right here. So our arguments to our functions are technically memory data. When a function is called, it is given some arguments, and then when the function is complete and exits, those arguments are essentially lost to the void, and we have no ability to go back and reference those arguments again. So the arguments would be a good example of a memory variable. Okay, so hopefully this first way of talking about storage and memory, I'm saying that in this case we're talking about storage memory as it relates to our contract data, makes a little bit of sense. And we'll see a better example of this as we work throughout this contract. But for right now, I just want you to understand that sometimes when we refer to storage and data, and you see these terms inside of documentation, it's talking about where our data is stored. So let's now take a break. We're going to come back and we're going to talk about the second context in which you see these terms. And this is by far the much more confusing one, but it's the one that is related to the error message that we currently see. So let's take a quick break and then discuss that in the next video. In the last section, we spoke about the difference between storage and memory in the context of where our contract stores some data. We're now going to look at the other side of the coin, which is the term storage and memory as it applies to how our Solidity variables reference values. All right, so you'll recall that we were back over inside of our create request function over here. Now figuring out what storage and memory are with relation to Solidity and all this stuff with this code snippet right here is a little bit challenging to understand. So rather than trying to explain what's going on with this code snippet right here, I put together a nice little tiny contract that's very easy to understand and will much more clearly illustrate the differences between memory and storage. So let's take a look at this contract. It's called numbers. It has a single variable, which is an array of integers called numbers. And inside the constructor function, we take that numbers array and push in the values 20 and 32. So if we were to now print out everything inside of numbers, I would expect to see something like 20 and 32, right? Yeah, that makes sense. All right, now here's where things get interesting. Right underneath those two lines, I'm going to add a new line in. And I'm going to write out a line of code that looks very similar to the one that we had just written over here inside of our contract. So I'm going to declare a new variable inside of a function and assign it a value. All right, so over here, I'm going to say that I'm going to declare a new array of integers. I'm going to call it my array, and I'm going to assign it the value numbers, like so. Now when I do that, I still have a warning over here. So if you look at the warning, the first one, it says variable is declared as a storage pointer. Well, that's definitely the same warning that we just saw over in our code. So it looks like there must be something very similar to what we did right here and what we did over inside of our contract. So I'm going to add in one additional statement or one additional keyword to this line right here that's going to make that warning go away. And then we'll talk about exactly what that keyword is doing for us. So right before my array, I'm going to add the keyword storage, like so. Now you'll notice that I still have a warning over here, but I only have one warning now, and it says unused local variable. That warning just means to say, hey, you declared a variable, but you never actually used it, which is totally fine. We don't care about that right now. Clearly, though, it resolved the earlier warning message that we saw, and the same one that we saw over inside of our contract as well. So what's going on with the storage keyword? What's its purpose? Let's take a look at a diagram that's going to help us understand that. Before I show you the diagram, though, I want you to remind you what we spoke about in the last video, which was to say that any of our contract level variables, like the one we have right here, is always stored inside of the storage area of our contract. Just a quick reminder on that. Okay, so now over to our diagram, right here. So here's our line of code, and I've broken it down piece by piece. At the very right-hand side of the equal sign, we have our numbers variable. And as we now very well know, that refers to an array of integers that is stored inside of the storage area of our contract. All right, so now here's the interesting part. When we use the storage keyword right here, it changes the way in which the new variable that we are creating right here, the variable called myArray, works. So this keyword changes how this variable works. When we use the keyword storage, it makes this variable point directly at the exact same location that the numbers variable is pointing at. So because we're using storage right here, the myArray variable will point to the exact same array. Now before I show you anything else, we're going to go back over to the Remix editor. I'm going to show you complete proof that that is the case. Okay? So I'm going to go back over to Remix, and right underneath this line of code, I'm now going to reference my array. I'm going to access the first element, and I'm going to set its value to be 1, like so. So let's now deploy this contract, and we'll retrieve the first element out of the numbers array. So I'm going to click create over here. I'm going to scroll down. Here's our accessor for the numbers array. Notice that this is numbers. That's this variable right here. It's not my array. We have no touch of my array right now. But if we access the first value inside of here, we get back 1. If we access the second value, we get 32. And if we try to get the third element inside of there, we get nothing, because there are only 2 elements inside of numbers. So at this point, after running that constructor, now this numbers array would look like 1 and 32, whereas before it was 20 and 32. So again, as soon as we use that storage keyword, it changes how this variable behaves. It makes this variable point at the exact same location, the exact same data structure. Now at this point you might be curious, well, why have we never really used storage before? And what would we use besides storage? Okay, yeah, that makes sense. That's where things start to get really interesting. So let's look at an example of what we might use instead of storage. So as you might guess, rather than storage, the other keyword that we can use right here is memory. If we use memory, it changes the way in which this variable behaves. In particular, if we use memory, some additional step is going to come into play. So if we executed this line of code right here with the keyword memory, we would take the numbers array, so this thing that's sitting inside of storage right here, we would make a copy of it, and let's just go through the whole process. Solidity would make a copy of it, and place it into memory inside of our contract. And remember, memory gets dumped anytime a function exits. And then myArray would no longer point at the array inside of storage. Instead, as you might guess, it's going to point to this new copy sitting over in memory. So the net result of that, well, let's run some code and see what happens. So over here, I'm going to change storage to memory, and then I'm going to redeploy the contract. So we're going to use this new code now. So I'm going to create, and now I'm going to look at the first element inside the numbers array. You'll recall that when we use storage right here, the value of the first element was 1. However, now that this is using the memory keyword, when I click on numbers, it's 20, which was what it originally was. So clearly, in this case, when we modify myArray, we are modifying a totally different array. Not the same array, totally different. Okay, so at this point, hopefully, maybe you don't understand why we care about the difference, and I don't blame you if you don't, but you might at least have some idea of how sometimes when we use the term storage and memory, it's talking about where we store our contract data. And then sometimes when you see the term storage and memory, it's talking about the variable declaration keywords storage and memory. And those are talking about how our variables store or reference values. Okay, so hopefully this part is clear right here. Sometimes when we use these terms, they mean one thing, other times they mean another thing. Hopefully that much is clear. But we still haven't really answered the question of why we care about memory or storage at all. Why do we really care? Well, let me show you a very good example of why we might care about these storage and memory keywords. I'm going to delete these lines of code right here, and I'm going to add a new function to our contract, okay? And I'm going to call this new function, let's call it changeArray, just keep it simple. I'm going to make it public. Actually, let's make it private, just to be very clear and say no one else, like we cannot directly call changeArray. Only other functions inside the contract can call this function right here. We're going to say that this array takes one argument. It's going to be an array of integers, and we're going to call that array myArray, like so. Then inside of here, I'm going to say that I'm going to take the first element inside of myArray, and I'm going to set it to equal to 1, just like we were doing it before. Now at this point, we are not calling changeArray in any way, shape, or form, right? If we create a new instance of this contract, this function will not be invoked. So let's change that. Let's add a call to changeArray inside of our constructor. So after we add these two values to numbers, I'm going to call changeArray, and I'm going to pass in the array numbers, like so. All right, so now here's where things start to get interesting. I want you to imagine in your head right now, what would happen if we deployed this contract and then accessed the first element inside of numbers? I mean, look at this. We're calling changeArray, we pass in the numbers array, and then inside that function, we update the value of the first element. So I want you to just take a wild guess at what it might be. All right, hopefully you've got some idea. I'm going to now deploy the contract. So here's the new version down here, and I'm going to retrieve the first element. So I think that you could agree with me, this first element is going to be either 1 or 20. It's definitely going to be one or the other. Okay, so I'm going to say run that thing, and sure enough, it is 20. So what does that mean? Well, it means that we passed in the numbers array, we received it inside of this function, we then modified that array, but that modification did not change the numbers array. What that means is that whenever we pass a value into a function like this, we are actually making a copy of that array. So changeArray, we're passing in numbers right here. When that array arrives as an argument inside of our function right here, it has been copied. So myArray is a total copy of numbers. And so we're kind of like in the situation back over here, where we have one copy of our array in storage, that's the numbers array, and we have one copy inside of memory. That's the myArray array. Whenever you take in function arguments, they are automatically assumed to be memory type variables. So it's assumed that you want to make a copy. It's assumed that you want this behavior right here. So if I wanted to, I could add in the memory keyword right here, and that would just make it very clear to everyone in the world that, yep, in fact, this is a memory variable. It is a copy. It's referencing an array that is stored in memory. However, if we wanted to change this behavior right here, if we wanted to make this behave differently, we could replace the memory keyword with storage instead. When we use the storage keyword in an argument list right here, it means do not attempt to make a copy of the array. Instead, take this numbers array and make exactly this array right here available inside the function. And so this takes us back to this earlier situation over here where we had storage, and that was referencing the exact same array. So let's now deploy this contract and see what happens. So I'm going to click create. I'm going to fetch the first element out of here, and you'll notice that the value is now 1 because my array is the exact same array as numbers. Same thing. So when we modify the first element, we are changing the first element of numbers. All right, so hopefully that makes it a little bit clear why we kind of care about these memory and storage keywords. It changes how we are passing around references to these data structures. Now, if you've never worked with a data structure, or excuse me, with a computer language that works with by value passing versus by reference passing before, some of this stuff might seem just like over the top, way more complicated than it needs to be. However, as you start working on your own contracts, sometimes you're going to end up writing functions where you want to pass in some data structure like an array, a mapping, or a struct. And in the function, you want to modify that data structure. So you want to change it, and you want to make sure that that new updated data structure is used from the original function that you had called it from. And so that would be a very good example of where you might want to use the storage keyword. Otherwise, if you're calling a function with a data structure and you don't intend to map it in any way whatsoever, then you don't need to add that keyword on. And you can just let Solidity behave as the way that it normally would and not have to sweat it at all. Whew. All right, so that's my spiel on memory versus storage. Again, at the end of the day, the big thing to keep in mind here is that sometimes we're talking about where data is stored, and sometimes we're talking about these how we are referencing these values with our variables. Two completely different subjects. Yes, they're very tightly coupled, but they are different. So when you start looking at documentation around this stuff, it's kind of challenging to understand because you just see these two terms right here thrown around willy-nilly. Now, you're probably wondering back here at create request, well, what keyword are we going to put on? What are we going to do here? How are we going to solve these error messages? We definitely have to put in either storage or memory inside of our variable declaration right here. However, in this case, it's a little bit more clear cut whether we want to have storage or memory. Here's why. Right here, we are creating a brand new request object. When we create a local variable like this, it automatically gets created in memory. Because remember, these are our storage variables. We don't have any other storage variables. So these are the only possible storage variables we can have. Do you see something inside of here that says, oh, I'm going to hold a single request, like only one request at a given time? Well, no, we don't have a variable for that. Yeah, we've got this thing that can hold many requests, but we don't have a variable that holds one single one. So this chunk right here creates a new request in memory. Because that request has been created in memory, this new request variable right here, it can't point to a version of this thing in storage. It can't. It doesn't exist in storage. All new request can do is attempt to refer to this new variable or this new value that exists inside of memory. So we have to use the keyword here, memory, like so. And when we add that in, you'll notice the error messages go away. Now, if you want some better proof of what we have to do here, if you try adding in storage, you'll see that we still have a warning or an error message here entirely. And it says type struct campaign.request memory is not convertible. So it's saying this thing right here is a memory value and it cannot be turned into a storage type value. So that's what that particular error message means. So yeah, we definitely need memory here. Whew, all right, we're done. That's it. That's all I have to say on storage and memory. I know this stuff probably seems ridiculous, very complicated. Honestly, at the end of the day, you probably aren't going to run into this problem too often, but if you do, at least you now have some idea of what it's all talking about. So let's take a break right here, and we're going to continue with our contract in the next section. In the last video, we finished up our create request function, and we're now ready to move on to approve requests. Remember, approve request is what a contributor will call whenever they want to approve or disapprove a given spending request. In this video, I want to lay out some considerations that we need to be aware of as we start to develop our voting system. So the voting system that allows people to say, yes, I approve this withdrawal of funds, or no, I do not allow it. So I want to lay out two big requirements right now for our voting system. These two requirements might seem like they're really obvious, but I want to make sure that you and I are 100% on the same page with respect to how the voting system should work. So here's big requirement number one of the voting system. Big requirement number one is that we should be able to make sure that a single contributor cannot vote multiple times on a single spending request. So in this diagram right here, you'll see that we're saying that Bill, Jane, and Alex are voting yes one time on the spending request, but it looks like Amanda is trying to vote no 3 times on the same request right here. Without a doubt, we absolutely want to prevent this behavior. A single contributor should only be able to vote one single time on any given request. So this definitely implies that we're going to need some system to keep track of who has voted on which requests. All right, so that's big requirement number one. Here's big requirement number two. All right, big requirement number two is that we should make sure that whatever voting system we come up with, it should be resilient for if we have many different contributors or many different approvers in our campaign. It's absolutely not unreasonable to expect that a given campaign might have hundreds or even thousands of different contributors or approvers tied to it. As a very practical example, here's a Kickstarter campaign that I just very randomly pulled up. This is a completely arbitrary campaign right here, and you'll see that it has nearly 7,000 people tied to it. So if we were going to start to use Ethereum and Solidity contracts to manage our Kickstarter campaign, well, we definitely need to make sure that it has the ability to work with this many backers right here. So that is absolutely a hard requirement of our contract. All right, so you might be kind of curious, well, you know what, Stephen, that seems like two very obvious requirements. Why do we care about that at all? Well, it starts to come down to how we place some design logic inside of our approve request function. So let's take a pause right here. Now that we understand these two big requirements, we're going to come back in the next video, and I'm going to lay out one possible way of designing our voting system. So let's take care of that in the next video. In the last video, we laid out two big requirements for our voting system. First, we should only ever allow a given person to vote one time on any request. Secondly, we should make sure that our voting system can accommodate many hundreds or thousands of different people voting. So with those two requirements in mind, I'm now going to show you one possible way of putting together the voting system. Now let me be really clear. I'm about to show you the wrong way to design this voting system. So you might be thinking, wait, Stephen, you're going to show us the wrong way? Why are you going to do that? That's just confusing. Well, I'm showing you the wrong way for a very good reason. The way that I'm going to show you to implement this voting system is how I expect you might decide to design the voting system on your own personal project. I want to show you how you might design it and why it's wrong. All right, so the entire idea here is I really think when you start on your own personal projects, you might design this voting system in a very particular way because it's the most obvious way, it's the easiest way to do it, and that way is wrong, just entirely wrong. It is a very bad approach inside of a Solidity contract. So I'm going to show you this wrong way first. I'm going to tell you why it's wrong, and then we'll turn back around and redesign the whole system in a much more reasonable and sustainable fashion. Okay, so that's the idea. Again, I know it's really annoying when I show you the wrong way of doing things, but this is a case where you really just have to be aware of these gotchas. So let's now dive in. I'm going to show you the wrong way of doing this. All right, so here's one way that we might start to lay out some data inside of our contract to address the fact that we want to have many people voting, and we also want to make sure that anyone can only vote one time on any given request. On the left-hand side, I've got the address array of all of our contributors. We've already created this object right here, this data structure. That is our approvers array that we already created. And that was an array of addresses, you will recall. So we've got that list right there of everyone who has ever donated to our contract. Then, to address the issue of making sure that people can only vote one time on any given request, maybe we create a second array that exists inside of each request struct. This address array right here might record the address of every person who has voted on this request already. So the address array will start off as completely empty, and then as soon as people start voting, we will add their addresses to this array. Whenever they vote, we will increment some counter of yes votes or some counter of no votes. And then anytime they attempt to vote in the future, we'll look at the person who is attempting to vote, we'll take their address, and we'll see if that address already exists inside this array. If it does, that means they've already voted once, and we should not allow them to vote again. All right, hopefully this system makes a little bit of sense. And maybe you will agree with me that, yeah, this seems like a pretty obvious way of doing things, right? I feel like it kind of does. Store two arrays, and here's a list of all the people who have contributed. Here's a list of all the people who have voted on this particular request. All right, so let's now take a look at how we might write our approve request function with this type of design. All right, so here's one possible way of implementing that logic. And you know what, let's look at it inside of Remix first over here. So this is one possible way of writing out approve request with that type of data structure. Inside of here, the first thing we do is check to see if this person has ever donated to our campaign. Obviously, if this person has not donated to our campaign already, then we don't want to allow them to vote. We won't go too far into the logic right here. Now, this is a for loop. We've not looked at a for loop inside of Solidity before, but it looks very similar to JavaScript. I think you'll agree with me. I bet you can understand what's going on. We first start off by assuming that this person has not donated. We then loop through our approvers array, and if that person's address, if whoever's sending the transaction's address is inside that array, we flip that isApprover flag over to true. And then after the for loop, we check to make sure that this person is an approver. So if they did not donate, we kick them out of the function. Then the second thing that happens here is we make sure that this person has not voted before. Here's our request struct. It has a list of people who have voted. We loop over that array and we make sure that this person's address is not present in there. If it is, they've already voted once already and we should kick them out. All right, so again, this is just one possible way of implementing approve request. And again, at this point, I think you'll agree that this seems like a pretty reasonable way of doing this implementation. Let's now take a break. We're going to come back in the next video, and I'm going to tell you very clearly why our current implementation of approve request right here is a very poor way of writing our contract. In the last video, we spoke about one possible way of implementing the approval system. Let's now talk about why this is a very poor approach. So we're going to take a look at a diagram. All right, so inside of our imaginary approve request function right here, I want you to make a little assumption with me. I want to assume that the logic that we placed inside this for loop right here, like this loop to check to see if the person who is sending the transaction is inside of that approver's array, and if they are, we flip this Boolean flag over to true. Let's assume that that entire operation right there costs 10,000 gas. So this if statement right here costs 10,000 gas. So in total, this for loop costs 10,000 gas for every person who has donated to our contract or to our campaign. And then in a very similar fashion, this require statement right here, maybe this costs 5,000 gas to execute. So the entire for loop down here costs 5,000 gas for every person who has already voted on this particular request. With that in mind, let's do a little math on exactly how our gas costs are going to scale. All right, so here we go. For one person or for one contributor, just to check to see if they are a member of our campaign, maybe that costs 10,000 gas. We have an additional 5,000 to see if that person has voted on that particular request. So in total, for one contributor, one person, doing this entire function costs 15,000 gas. All right, that seems reasonable. We've spoken about gas and we've said that it's the cost that it takes to execute some lines of code inside of our contract. And we haven't spoken that much about how gas really costs, but let's just imagine, sure, 15,000 gas for one person. So let's now take that other requirement we had over our voting system. Remember, the other requirement was that we should have a voting system that allows for many thousands of contributors inside a single campaign. So what happens to our gas costs when we start to imagine a campaign with thousands of people? How do our gas prices increase? Let's imagine that we have 10,000 contributors now. So if we have 10,000 contributors, we have to run that first for loop 10,000 times. And that if statement that we were executing cost 10,000 gas. And then for that second check, we are now doing that require statement that costs 5,000 gas, potentially 10,000 times. In total, with 10,000 contributors inside of our contract, we could now be spending 100 million gas. So as every single person signs up or donates to our campaign, we are incrementally increasing the cost of our approve request function by 15,000 gas every time. So as soon as we start to get a very popular campaign, maybe with 10,000 people, we might be having to spend a tremendous amount of money in order to call that approve request function. So that is why this is a very poor approach. That is why using an array for our addresses out here and an array for our addresses inside of a given request is a very poor approach. This is a case where we are designing a contract that has an array that grows unboundedly. So we have written our contract in such a way where we have to assume that this array of addresses right here is always going to grow without bound. And we don't have any way of restricting the size of the array. And in fact, for the purposes of our contract, we probably don't want to restrict it, right? In theory, we want to allow as many people to donate to our campaign as possible. So it would be really bad for us to start to add some logic to somehow cap the number of people who can contribute, and thus cap the number of addresses that we store. This is a problem that is not only related to this voting system that we've put together, but to any type of a use of an array data structure in a contract. If you are storing data inside of an array, and then you have some logic that eventually loops over that array, you have to be 100% sure that your contract is never going to end up with that array growing tremendously. Because if it does, and then you start to iterate over it, you might be signing yourself up to pay some tremendous amount of money in gas. So in closing here, the entire idea behind our voting system as it stands right now is that it is way too expensive because we have these array data structures that we have to loop through to see if someone has voted before and to see if they have even donated to our contract. And because we are looping through that contract, we have to spend a tremendous amount of money as more people are introduced. Anytime you start working on your own personal contract, I'm going to very, very much encourage you to avoid working with arrays wherever possible. So of course, this kind of comes full circle now, where I had said previously that this approvers array of addresses right here was something that was a poor way of addressing our voting system. And so we are going to update this data structure right here to use a slightly different data structure that doesn't require us to iterate through every record inside there to see if someone has contributed already, or see if someone has donated to our approved a given request already. All right, so hopefully that's a little bit more clear, and hopefully that makes it a little bit more obvious why our current design of our approvers array and why the current design or the design of the voting system I just laid out is not a good approach. In the end, it just costs way too much gas, way too much money, and it might eventually cause our contract to not function anymore. So let's now take a quick pause. We're going to talk about how we can address this and some other data structure that we can possibly use to make sure that we are still able to handle many people inside of our contract, but also implement the requirement of only allowing one vote per person on a given request. So we'll talk about that alternate design in the next video. In the last video, we spoke about how this approach to the approve request function doesn't quite work out. Remember, it all comes down to the fact that we are using arrays to store these addresses, and those arrays are growing without bound. Because we are always going to iterate through the full length of our arrays, we might end up having to spend a tremendous amount of gas in order to look up some given address inside of the approvers array and the array that keeps track of who has voted on a given request. We're now going to pivot and start looking at the solution that we're going to actually use inside of our contract. So we looked at the way in which these things don't work out. We looked at the problem. We're now going to look at how to solve it. So everything from here on out is the right way of writing this code. In order to solve this issue, we're going to stop using arrays altogether inside of our contract. And we're going to instead use a slightly different data structure. The data structure that we're going to use for storing all these addresses, rather than being an array, is going to be a mapping. We spoke about mappings a little bit many videos ago. A mapping is a reference type that is available to us inside of Solidity. You can think of a mapping as being like a collection of key value pairs, and so effectively it's very similar to a JavaScript object. There are some very discrete and definite differences between a mapping and a JavaScript object, and we'll talk about exactly what those differences are in just a little bit. First, however, I want to talk about why a mapping is going to solve our issue here. Okay, so let's talk about exactly why it's going to solve our problem. So it all comes down to the search time for each of these data structures. Before, we were using an array, and we're now saying that we're going to use a mapping. In computer science lingo, we can say that whenever we want to try to do a search or find some piece of data inside of an array, the best case that we can get for running that search will be linear time. Again, this is a little bit of computer science lingo right here. When we say that search inside of an array is linear time, that means that for every additional record that we add to this array, it's going to take a slightly larger amount of time to execute a search. So if we have 10 records inside of an array, it might take 10 seconds to search through. And if we have 100 elements inside of an array, it might take 100 seconds. In other words, the size of the array dictates how long the search is going to take. And that's exactly what ran us into some trouble in the last video when we started thinking about gas prices. The big difference between an array and a mapping is that doing a search inside of a mapping is what we refer to as constant time. That's another piece of computer science lingo. When we say constant time, that means to say that no matter how many pieces of data we are storing inside this mapping, it's always going to take the exact same amount of time to execute a search. So in other words, if we have one contributor inside of our campaign, it might take just 1 second to look up that given contributor. If we then later on have, say, 10,000 contributors inside of our mapping, it's still going to take only 1 second to look up a given contributor. So it doesn't matter how many people enter into our contract, it's always going to take the same amount of time to check to see if they have donated and check to see if they have already approved or disapproved a given request. So that's why it's going to solve our issue here. It all comes down to the computer science-y part of these data structures. All right, so clearly we definitely want to use mappings here. Let's pause right now. We're going to continue in the next video, and we're going to start to discuss exactly what mappings are and how they differ from traditional JavaScript objects that we might already be used to. So let's take care of that in the next video. In this video, we're going to take a look at a couple of the big gotchas around mappings. Again, in general, we can consider them to be like JavaScript objects, but they are different in some very specific ways. Let's first take a look at a normal JavaScript object, and I want you to see some of the things that we can do with a JavaScript object very easily. So I've got a little code snippet over here. Inside this little editor that I'm using, I can put some code in on the left-hand side, and then if that code produces any output, it'll automatically print on the right-hand side. So for example, if I type in the string, "hi there," you'll see that it automatically appears on the right. And if I paste that string several times, I get this identical output here on the right-hand side. So we're going to use this editor just to give you a quick review on some very common operations that we can use with JavaScript objects. Inside of here, you'll see that I've already got an object, and it lists out a little bit of a Spanish to English dictionary of sorts. The keys of this object are English colors, like red, green, and orange. And then on the right-hand side are the equivalent words in the Spanish language. So red in Spanish is rojo, green is verde, orange is naranja. I'm hoping I do my pronunciations there somewhat reasonably. If you're a Spanish speaker, I hope I didn't just butcher these words. Anyways, the point here is that with a JavaScript object, we can make use of a couple different methods to manipulate this object. In particular, I can use the method object.keys and then pass in Spanish colors like so, and I get back an array of all the different keys that my object has. Likewise, I can write out object.values and pass in Spanish colors, and I get out all the values. Another way that I very commonly might manipulate a JavaScript object is to say something like Spanish colors and then use bracket notation to access a particular key inside there. So I might say something like red, and that returns the value at key red, like so. One other thing that you will recall is that if I try to access a key that does not exist, this object will return the value undefined. So for example, if I put in that right there, I get back undefined, which in this editor prints as nothing. But if I put down equals 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 undefined, it says true. So clearly, yes, this does return undefined right here. So in total, we just walked through 4 very simple operations. Firstly, clearly we can easily retrieve all the keys that a JavaScript object has. We can easily retrieve all the different values that the object has. We can retrieve a single key, like so, by using the bracket notation. And if we try to access a key that is not defined, we get back a value of undefined. So with those 4 rules in mind, let's now go take a look at mappings with Solidity and get a better understanding of how they work. All right, so we're going to look at a couple diagrams here. Here's the first one. So I'm going to lay out a couple of big gotchas around mappings I want you to understand. And these are going to be in stark comparison to how JavaScript objects work. So the first big gotcha that we need to be aware of around mappings is that keys are not stored with mappings. Keys are not stored. And that might seem like a very strange thing to say. If we go back over here to JavaScript land, you and I very well know that we had just said a moment ago object.keys with Spanish colors, and that retrieves all these keys right here. So the same is not true with mappings. With mappings, we are working with a classic data structure called a hash table. With a hash table, we have something called a lookup process. So over here on the right-hand side, you can see the underlying data structure that represents our mapping, in this case with values of rojo, verde, and naranja. In order to look up some different value from this mapping right here, we have to provide a key ahead of time. We provide this key, the key gets passed to a hashing function, and the hashing function outputs some predetermined index. So maybe in this case, index 3. When we get this index 3 right here, Solidity then knows to go to index 3 inside the mapping and retrieve the value from that element right there. So in a Solidity mapping, keys are not stored. That means we cannot get a list of keys. We can't access them. We don't know what keys a mapping has. So if we start to define an object or a mapping inside of Solidity that looks like this right here, you and I cannot know after the fact whether or not red, green, and orange are defined keys unless we try to go and access those values. We can't get a list of these. We can't get a list at all. And this might sound like maybe a strange thing, maybe a weird thing. As soon as we start to write some code inside of our contract, I'll show you why this is a very relevant thing, and hopefully at that point it'll also make a little bit more sense. Now the next thing I want you to be aware of with mappings is that values are not iterable. In other words, we cannot loop through a mapping and print out all the different values that it has. This is very closely related to the fact that we just spoke a moment ago about how keys are not stored and we cannot access a list of keys. So in other words, if we have a mapping, we cannot write, say, a for loop that iterates through all the values. We cannot run any type of function or do any type of call that somehow says, okay, go into this mapping and retrieve all the values that exist. So like you just saw a moment ago, back inside the JavaScript world where we said object.values and got a list of all the values like so, we do not have this functionality inside of Solidity. We cannot get a list of all the different values that a mapping has. All we can ever do is do a lookup of values, like we saw just a moment ago by writing out something like Spanish colors, red, like that. So in other words, these mappings are only good for single value lookups. They're not good for storing information that we want to iterate over sometime in the future. Now the next thing that's going to be a little bit surprising with mappings is that we say that with solidity mappings, this is kind of like a quote that we use, we say that all values exist. So again, just a moment ago inside the JavaScript code editor, we saw that if we wrote out something like this, we got back undefined. So specifically a value that tells us, hey, that value has not been defined inside of this object before. The same is not true of mappings. So in other words, if I take that same Spanish colors object, convert it to a mapping, and then try to look up the key, say, Amarillo on it. Amarillo, which means yellow, by the way, or I guess so really this should be yellow because the keys were English. Anyways, if we put in yellow to the hashing function, we'll get back some index again. The index will be looked up inside the mapping. And rather than telling us that there is no value at that particular index, we will actually be returned some default value for that element right there. If these were all strings, then the default value would be empty string. So if we were to convert this to the JavaScript world, that means to say that if this was Solidity code right here, and we looked at Spanish colors and then tried to look up a key that does not exist, we do not get back undefined. Instead, we would get back an empty string. This default value that we get back from mappings depends on the value type of the values inside of our mapping. If these were not strings inside of our mapping, if they were instead, say, integers, then we would get back a 0 value for an integer, which in this case would be literally the number 0. So what this means is that in practice, it kind of makes it really challenging for us to decide whether or not a value exists inside of a mapping. Like, think about it. If you're storing numbers inside of a mapping as values, and you want to say, oh, do I have some value for the key red or the string yellow or something like that? Well, if you look up that yellow string inside the mapping and you get back the number 0, that kind of makes it challenging for you to decide whether or not, yes, that value already exists inside the mapping and it was set to 0, or no, that never existed inside of it and we just got back 0 because that's the default value. So in other words, the point here is that when we start to look up values or keys inside of a mapping, it's kind of tough to decide ahead of time whether or not that value actually exists or not. And I think there's one last thing. Here we go. So last thing, understanding all this mapping stuff now, here's the final diagram of how our campaign contract is going to be laid out. So this is really the final design. So because mappings have the benefit of this constant time lookup, and we want to make sure that our contract can be used with many, many, many different contributors, we're going to do a little bit of a refactor. We're going to say that the approvers property is not going to be an array of addresses anymore. Instead, we're going to say that it is a mapping. It's going to be a mapping where the keys are addresses and the values are booleans. We'll know whether or not someone has donated to our campaign by looking up their address inside this mapping, and if that lookup returns true, then we'll say, okay, this person must belong. And maybe that might not make a lot of sense just yet, but as soon as we write the code for that, it'll make a lot more sense. And then a very similar thing, inside of our request struct, we're going to add on an approvals mapping. So this is a mapping that tracks who has voted on a particular request. And then to track whether or not it's a yes vote or a no vote or anything like that, we're going to have a separate counter that counts the number of people who said yes. Now this part right here, this approval count, might be a little bit surprising. You might be thinking, well, why don't we just store whether or not someone does a yes or no vote in this approvals mapping right here? Well, remember, when we're working with a mapping, we cannot iterate through the mapping. So it's kind of pointless to store whether or not someone voted yes or no inside this mapping right here, because we can't iterate through it and try to total up all those values. Instead, we have to keep this separate counter around to track whether or not a person voted yes or no. All right, so that's a lot on mappings that we've now discussed without even looking at some of the basic syntax around it. So we still have a lot to learn about mappings. Let's take a pause right here and continue in the next video and start implementing this refactor. So quick break, and we will start that in a minute. In the last video, we spoke about how we're going to replace our arrays with mappings in the goal of solving some of the scalability issues of our contract. The first thing we're going to do inside of our campaign contract is to replace the approvers array variable right here. So we don't want to work with this array of addresses anymore. We want to work with a mapping instead, because with a mapping, we can add as many different values that we want to this thing, and we don't have to worry about taking a long time to loop through it in the future, because we always get the benefit of that constant time lookup. Now, to give you a good idea of what this variable is going to look like after we refactor it right now, let's look at a quick diagram. So here's our contract. We're going to define a mapping where the keys are addresses and the values are booleans. And we're going to call that mapping the approver's variable, exactly what we call it right now. The keys of this mapping are going to be addresses of people who donate to our contract. And then the values will always be a boolean that will always set to true. True indicates that this person has in fact donated to our contract. Now you might be curious, why are we marking this thing specifically like as true? Why don't we do like false or something like that? Well, remember we spoke about just a moment ago with respect to default values inside of a mapping. So whenever we try to access a value inside of a mapping, we say that all values exist. And if we try to access a key that we have never worked with before, we'll get back some default value. In the case of type Boolean, the default value is false. That means that if we at some point in time tried to look up an address of, say, like 0xAB8519, which clearly does not exist inside this mapping, if we looked up this address inside this mapping right here, we would get back a Boolean of false, rather than anything like, say, undefined or null or anything like that. So we're specifically putting true here so that we can actually differentiate when we are accessing an address that already has been defined inside the mapping. Now, the last thing I want to remind you here, inside this diagram, I'm showing a listing of these addresses. But to be clear, again, we don't actually store these addresses or these keys with the mapping at all. So they don't actually exist. Instead, we have some type of kind of abstract mapping here that says, well, if you plug in address 80x1787, that would map over to this value of true right here. So although my diagram might show these addresses, they don't actually exist inside the mapping. All right, so let's do this refactor now. So back inside of our contract, I'm going to find the approver's line. We're going to delete that entire line, and we're going to replace it with our new mapping definition. We've already seen the syntax for defining a mapping several times, whether or not you've actually realized it. So to define a mapping, we write out the keyword mapping. We write the type of key that we want to have. So that's going to be an address for us. And then we write out a big arrow and then the type of value. And in this case, we want to have a Boolean. We can then write out public, and then we'll label the variable like it was before as approvers. Now, immediately after doing this, we'll see an error message appear down inside of our contribute function. Inside of here, we're trying to call approvers.push. Push is a method that is only available to arrays, not to mappings. So we need to now refactor this line right here to work with a mapping rather than an array. Notice how right now we're taking the address of the person who is sending in this transaction and adding them to the approver's array. So we want to make sure that we add this address to our mapping and give it a value of true. And that will mean that if we ever look up this address inside the mapping in the future, we'll get back a value of true and know that this person has in fact donated to our contract. So let's delete this line. To work with mappings, we use syntax very similar to JavaScript objects. So we can write out approvers, we can write out our square braces, just like we would with JavaScript, and then we put inside of here the key that we're trying to access. So we're trying to look at the key of message.sender, like so. And we're going to set that thing's value to be true. So this adds a new key of this address to the approver's mapping and gives it a value of true. Now, just one last time, I want you to remember this address does not get stored inside the mapping. Only the value true actually does. Okay, so that's pretty much it. Now, at any point in the future, we can very easily check to see if someone has contributed to our contract by writing one simple line of code. For example, if we want to make sure that in order to call create request, you have donated to the contract, we could add a line of code inside of here that simply says require approvers message.sender. This will look up our approver's mapping. It will try to access the key of this address inside of it. If that person has donated to our campaign, this entire little block right here should return true, and then we're going to require that that is in fact true. So if this person has not been added to the approver's mapping, it'll return false, require will fail, and they'll get kicked out of this function entirely. So as you can see right here, this is a lot easier to work with for doing existence checks like the one we want than the kind of for loop that I had showed you previously over right here. So rather than writing this complex for loop right here that might cost some variable amount of gas for every entry inside the array, we write that one simple little block right here to do the entirely same exact thing. So this is exactly why we are using a mapping rather than an array to store all those addresses. Okay, now we don't actually need this check inside the create request function, so I'm going to take that out. It was just a quick for example. So that little refactor there looks good. Now the next thing we're going to do is to refactor our request struct up here to add in the idea of keeping track of who has voted on a particular request as well. And just like we did with approvers right here, we're going to use a mapping for that as well. So quick pause, and we'll take care of that in the next video. In this video, we're going to update our request struct to add on a mapping called approvals. This mapping is going to be very similar to the approvers mapping that we added as a state variable to our contract. Approvals is going to track whoever has voted on a given request. So every instance of a request struct inside of our campaign will have its own separate approvals mapping. It'll have the same exact internal type as well, where the keys are addresses and the values are booleans. So let's give this a shot. Back inside my Remix editor, I'm going to find my request struct, and then underneath the complete flag right here, we'll add on two new fields. The first one is going to be a uint that keeps track of the number of yes votes that this request has received. So we'll say approval count like so. Notice that we're not going to keep track of the no votes here. In truth, the no votes don't really matter for us at all. The only thing that really matters is the number of approvals. We're going to eventually make a check to say that, hey, are there a number of approvers that are greater than, say, 50% of the number of approvers who are in the contract? So if this thing gets an approval count of over 50% of the approvers, then we're going to say that the request is valid and should be approved. Then immediately after that, we'll create the mapping that is going to keep track of whether or not someone has voted on a given request. So we'll say mapping, address, the arrow, bool, and then approvals, like so. Now the name approvals right here is not the clearest thing in the world, I think. This might be able to use a little bit better naming than approvals, just because it kind of conflicts with approvers down here. I called it approvals to say, hey, these are the people who have provided approvals of this request right here, but maybe we could rename this to something a little bit more reasonable. Okay, little misclick there. So now that we've got this mapping, we can start to work on our approve request function. So let's take a quick pause. We're going to come back in the next video and we're going to start working on that function. In the last video, we refactored our request struct to add on the approval count and approvals mappings fields. Now there's one quick thing that we missed in that last video when we did that refactor. If you scroll on down to the create request function, you'll notice that we now have an error on line 35 or so. And it says that we have the wrong number of arguments being provided to the request struct. Remember that every time we create an instance of a struct, we have to initialize every field of the struct. So because we added that approval count property, we have to add it to our list of fields here. So I'm going to add on approval count and initialize it to the value 0. Now you're probably very quickly curious why we did not have to also initialize the approvals field. There's a very good reason for that. When we initialize properties of a struct, we only have to initialize the value types. So these are all value types right here. We do not have to add any code to initialize a reference type, and a mapping is a reference type. So we don't have to add this to the line where we create the new request. Before we move on, there's something quick I want to mention about the approval count number right here, because I realized I wasn't entirely clear on exactly why it exists when we added it in the last video. All along in this contract so far, we've been saying that people have to vote yes or vote no to a particular spending request. So we've been saying either you say yes or you say no. However, for the actual implementation, we don't actually have to keep track of the number of people who vote no. When we eventually add some logic to decide whether or not a spending request is ready to be dispersed to the vendor, we are really only going to compare the number of yes votes against the total possible number of votes inside of a contract. So we don't have to actually include the number of no votes in that. Essentially, not voting at all is equivalent to a no vote. All we are really looking for is some minimum amount of consensus from our contributors, some minimum number of people who are saying, yep, it looks good to me, send this out. So really, we don't need any difference between voting no and not voting at all. So because of that, our request struct is only going to record the number of people who vote yes. You're not going to call our approve request function. Remember, that's what we are about to write. So when you call our approve request, that is specifically to vote yes on a request. And we're going to have no other function that allows you to vote no or anything like that. Okay, so now that is a little bit more clear, let's continue the next section where we are going to finally put together the approve request function. After a lot of back and forth, we're now finally ready to write approve request. Now, one thing I want to remind you about this function is that its goal is to approve a specific funding request. Our contract stores an array of request structs inside of the request variable. So we need to make sure that whenever someone calls the approve request function, they specifically tell us which request they are attempting to approve. To do so, I think we can use a little bit of approach like this right here. So let's say that on the right-hand side, we have our array of requests as a variable called requests. And inside that, maybe we have request A, B, and C. Then maybe Bill over here wants to try to approve request B. So Bill wants to target this one right here. In order for Bill to tell us which request he's trying to target, we're going to say that whenever you call approve request, you have to pass in the index of the request you are trying to approve. So in this case, Bill passed in an index of 1. Request A is at index of 0. Request C is at index of 2. And request B is at index of 1. So because Bill was trying to target request B, he's passing in the number 1 to approve request. Now, one thing you might be curious about here is the fact that we are using an array for handling our requests at all. You might be thinking, Stephen, aren't we going to run into the same issue that we ran into with arrays around our addresses? Isn't this thing going to grow and we're going to eventually have to pay a lot of money in gas? Well, remember, the whole concern around that array of addresses was that we had to do some search through that array. We were searching for a value in the array. But in this case, we are not searching for a value in the array of requests. We are doing a lookup. A lookup operation on an array is a constant time operation, just like it is a search on a hash table. So because we are not iterating through the array of requests right here, we're not writing a for loop or anything like that, this function right here will always be constant time lookup with the requests array. So because of that, because we are not iterating through our array of requests right here, we don't have to worry about any issues around runtime or anything like that. Okay, so with that in mind, let's now flip on over to our code editor, and we're going to create the approve request function. So back inside of Remix, I'm going to go back down to the very bottom of the contract, and I'm going to add on our new function called approve request. I'm going to label as public, and I'm going to make sure that I provide a unsigned integer that we're going to use to specify which request we are attempting to vote yes on. So I'm going to say that we're going to get a uint that we're going to call ID. And actually, you know what? Let's just be really clear and call it index. This is the index of the request that we are trying to approve. Now inside of here, we need to write two quick checks, you'll recall. The first check we have to add in is to make sure that this given person who is trying to do this approval right now has not, or excuse me, the person has already donated to our contract. So that's check number one that we were previously doing with this big for loop. And then check number two, we have to make sure that this person has not already approved this given request. So back inside of Remix, we can first start off by making sure that this person is a donator by saying require approvers and then look up message.sender. So we are requiring that inside this approvers mapping, if we pass in message.sender, we should get back a Boolean of true. If that is not the case, if we get back false because we passed in an address that we've never seen before, then this function will exit instantly. Next, we'll add in another require statement to make sure that this person has not voted on this particular request before. To access the requests that we actually care about here, we can look at the requests array at the given index. This request struct right here has a property called approvals. Remember, up here inside of our request struct, we have the approvals mapping that lists or records whether or not a given address has voted on this thing yet. So we will access the approvals property, and inside that thing, we're going to look up and check to see if the address of this sender has been added to the mapping. So we'll look up message.sender. Now, if this person has voted on this particular request already, then this statement right here will probably want to have return true. But remember, require statements will allow truthy values, and they reject or exit when they're given a falsy value. So we're going to add on a not in front of this. So this will say if this person has already voted on this contract and their address exists inside this mapping, that will return true, and we want to flip that to a false. So if it's falsy, we're going to immediately kick the user out of this function call. Then after this, we can place the actual logic to attempt to add this person's address to the approvals hash, or excuse me, the approvals mapping, and we'll also increment our approval count as well. So we can say requests at index, again, that's the request that we actually care about, dot approval count plus plus. So we're using the incrementer operator right here to make sure that, yep, we do in fact increment the number of approvals that we have. And then chances are that right before that, we probably want to make sure that this person is marked as having voted on this particular request. So right before it, we will also access that same thing. We'll get the approvals mapping. We'll say at message.sender, we want to assign the value true. So now if this particular sender ever calls approve request again with the same index, they would then fail this second require check right here. Now, the last thing I want to mention here is that we are accessing the request mapping 3 times in a row right here and doing a lookup operation. Rather than doing that 3 times in a row, we could probably assign it to a local variable instead. So let's take out request.index and assign it to a local variable that we'll create right here at the top of the function. Notice one thing I haven't said very explicitly, require statements can take place at any place within inside of a function. We don't have to put them as the very first line. So we can do a little assignment up here if we want to. So I'm going to say request, and we're going to mark this thing as a storage variable, very important because we want to manipulate the copy of this struct that exists inside of storage. We don't want to make a copy of it over to memory, and we'll call it request. And that's going to be coming from requests at index, like so. Now, if we hover over this thing, you'll see it says unused local variable. That's totally fine. We just have to make sure that we actually make use of request somewhere inside the function. So now we can go back to where we were doing the lookup inside the mapping and replace that with request. We can replace it here, and we can replace it here. Okay, so that's looking pretty good. Let's pause right now. It took us a long time to get to this point. So let's pause here and continue in the next video and test our code and make sure it's working the way we expect. It took us a long time to put together the approve request function, so I think that we would be well served to quickly test it out inside of our Remix editor. I'm going to pull open the right-hand side nav bar. I'm going to make sure I've got run selected, and I'm going to make sure that I also am using the JavaScript VM environment. I'll then make sure that I delete any existing instances of the contract that I've already deployed down here towards the bottom. And after doing that, I'll then set a minimum contribution. In this case, I'm going to use simply 0 minimum because I don't really care to test the minimum contribution right now. And I'll click on Create. So here's the new instance of our campaign contract. Now back up at the top, we need to make sure that we do some initial donation or contribution to our campaign so we get marked as an approver. I'm going to donate, how about like, I don't know, well, let's just donate, how about 1 Ether? That's totally appropriate. So I'll set the drop down to 1, or to Ether, excuse me, and I'll enter a value of 1. And then back down on the contract, I will contribute. In the console down here, I should see a transaction appear, and I should definitely not see an error message or anything like that. So now we can attempt to create a request and then attempt to approve the request as well. To create a request, we have to get first an address of where we want to send some money to. So to get another address, I'll go back up towards the top. I'll find the account dropdown. I'm going to select the second account on the list and copy the address. So I just copied it like so. Then I will toggle back to my manager account because remember, only the manager can create a new request. All right, so now we can go ahead and create the new request. Here's the button, and we have to enter in a couple of different arguments. So we need a description, a value, and a recipient. For a description, I'll say buy batteries. Make sure you place that inside of a string. For the value, right now we have not really specified whether this is Ether or Whey or what. So I'll just put in some numbers here. And then finally, for the address, I'll put my quotes down and paste the address in. And make sure you wrap that address in quotes. Now I should be able to click Create Request and see that new request created, excuse me. I should be able to also retrieve that request out of our array of requests. So if I enter in a 0 and click the button, I should see a description, the value, the address recipient. It should be marked as false, not completed. And then the approval count, excuse me, should start off as 0. Notice that we did not get back any information here for a mapping. So really, there's no way to retrieve and try to return an entire mapping. Remember, we cannot iterate through the keys or the values of a mapping. It is solely a lookup object. So even though we can use it to store many records, we can't use it to, say, iterate or return many records. The next thing I want to do is to attempt to approve that request. So I want to approve that one, and then we should be able to verify that approval count goes up by 0. So if I scroll back down to approve request right here, I want to approve the request at index 0. So I'm going to enter in a 0, and then I will click on Approve Request. Okay, so that looks good right there. Now if I try to retrieve the request at 0 again, oops, let me get some more space so I can actually, you see I put in 2 zeros, I just can't really see the text when I'm so zoomed in. So I'm going to get the request at 0, and you'll notice that now I've got an approval count of 1. So that is definitely working out. We are definitely now able to endorse or approve a request. However, if I try to approve that request a second time, so this will be the second time I try to approve it, which we definitely do not want to allow. I'm going to clear out my console here really quickly, and if I click on Approve Request again, I will see a nice big error message. And this error message is coming from our require statements right here. In particular, this one is probably coming from the second require statement that says, hey, you've already voted on this thing, you cannot vote a second time. We can also very quickly test the earlier require statement, or the first one on here, if we change to a different account, so any other account inside this list which is not marked as a contributor, and then try to call approve request again with an argument of 0. So I'll clear out the log here really quickly, click on Approve Request, and again you'll see a nice big error message. And this one is coming because I have not yet donated to this campaign. All right, so that's awesome. I think that we're making great progress here, but we still have a little bit of work to do. We have to make sure that after a request has been created, let's see, where's our diagram? Here we go. So after we've created a request and it's gotten enough approvals, we have to finalize it. So we have to make sure that the manager has the ability to actually process the request and get the money from it distributed to the recipient. So let's start taking care of that in the next video. The last thing that we have to do inside of our contract is put together our finalize request function. Remember, this is what a manager will call in order to finalize a request, or in other words, get the request paid out to the vendor. In theory, a manager should only be able to call this after a request has gotten enough votes. Let's now flip over to Remix and start putting together this function. At the very bottom of our contract, I'll add on finalize request. I'm going to mark this as public, and I'm also going to add on the restricted modifier as well, because of course we only want our manager to call this. Whenever someone calls finalize request, they need to also specify which request they're trying to finalize, just as we did before inside of approve request. So as an argument, I'm going to say that this has to be called with some number that specifies the index of the request that the manager is trying to finalize. Then inside of here, we can start doing a couple of basic checks. The first thing that we'll want to check is to make sure that this request is not already marked as complete. So if we go up to the top where we have our struct definition, you'll recall that it has this complete flag right here. It's a Boolean that starts off as false. Whenever a request is finalized, we're going to mark it as being complete. And we're going to do that by flipping this field right here to true. And that's going to make sure that people are not able to approve the same request, or finalize the same request multiple times. So after this thing goes to true, that's it, no more finalizing the request. So back down inside of our function, we'll add on require, and we're going to require that requests at index is complete. Now, specifically, we don't want it to be true right here. So again, we're going to add on the not right here to flip the Boolean from true to false. So if this thing right here is true, we want to flip that to false so that the require statement fails. Also, let's not forget to put our semicolon after that. Now, before we move on from the complete flag, we definitely want to make sure that we update the flag to be true after paying out this money to the recipient. So I'm going to make sure that right now I add in requests at index.complete is true. Already we're seeing that we are reaching into the request mapping several times here. So again, I think that we'll create another local variable just like we did before. So right underneath the top of the function, I'll add on request equals requests at index. Don't forget to also add in the storage keyword right here, because we want to specifically say that this is a variable that should be looking at the same copy of the request that already exists inside of storage. One other thing, just as a quick reminder, remember that the capital R right here specifies that we are about to create a variable that is going to refer to a request struct. Then inside of here, we can update requests at index to be simply request, and requests at index to be simply request. We do have an error message right now. If you hover over it, you'll notice that we've got, oh, did I misspell unit? It should be uint. My mistake. Okay, so this looks good. Now the next thing we have to figure out is how we decide whether or not a request has gotten enough approvals. And that's something that we have actually not really discussed much at all. We have said that every request object has a approval count value right here, right? It's a unsigned integer, but we haven't really specified how many approvals the thing needs before it can be finalized. So I think that maybe a reasonable approach would be to say that at least 50% of all the people who have contributed to this campaign have to vote yes in order for this thing to be finalized. So I think that we need to add on another require statement that compares the number of approvals that this request has against the total number of people who have contributed to the campaign. Now the second part of that, getting the number of people who have contributed to the campaign, is actually kind of challenging. Remember, right now, our array, or excuse me, our contract has a approvers mapping, and we cannot do any type of iteration or summation or anything like that over this mapping. So if we want to get some count of the total number of people who exist inside this mapping, we have to actually create a second variable or another state variable to keep track of how many people have joined in this contract. So I'm going to decide to add in another state variable here. I'm going to make this an unsigned integer as well. We're going to call it approvers count, and we'll make it public as well. So now every single time someone donates to our campaign, we're going to increment the value of approvers count. I'm going to find the contribute function. Here it is right here. And after we add that person's address to our mapping, I'll increment the approvers count variable by saying approvers count plus plus, like so. So now we will always have access to this variable that tells us how many people have joined in or contributed to our contract. Now that we have this number, we can finish the voting logic or the finalize logic inside of finalize request. So inside of here, we'll add on one more require statement. We will require that request.approval count is greater than approvers count divided by 2, like so. So now if we have, say, 50 approvers who have, or 50 people who have contributed to our contract, at least 25 of those, or actually 26 because it's greater than as opposed to greater than or equal to, at least 26 people must approve a request before it can be released. Now the very last thing we have to do is to make sure that after we run all this logic, we're finally going to take the money that is specified inside the request and attempt to send it to the recipient. For that, we'll write out request.recipient. Remember, this is the address of the person that we want to send our money to. Because it is an address, it has a method called transfer. And we can call transfer and pass in the amount of money that we want to send. So then inside of here, the amount of money that we want to send is request.value. So remember, the struct that we are working with all along has the value property, and that specifies how much money we are trying to send. So we'll say request.value, like so. Okay, I think that's pretty much it. Now, last thing we have to do is one more test of this contract. So let's take care of that in the next video. And then we can start thinking about actually deploying and building a real application in front of this contract. So let's take care of that in the next video. We've just about wrapped up our contract, but before we move over to writing any front end or anything like that, I think we should do one last quick test inside of Remix. I'm going to open the right-hand nav. I'm going to make sure I have JavaScript VM selected. I'll make sure I have deleted any other instances. Then I'll set a minimum contribution of 0 and click on Create. All right, so here's my instance. Of course, the first thing we have to do is to contribute to it. So I'll set a value of 1 Ether, and then I will contribute to the campaign. Next, I'm going to try to create a request. And of course, anytime we make a request, we definitely have to get an address of the recipient account. So just like we did previously, I'm going to select another account. I'll copy the address, and then I'll swap back to the manager account. Then I can go down to create request. I'll enter in a description as a string, and I'll give myself a little bit of space so you can very clearly see what I'm adding. So I'm going to add on a description of buy batteries. I'll put in a value of just some arbitrary amount, and then as a string, I'll add in the address as well. Make sure you wrap that with quotes. I can then click create request, and that should definitely create the request for me. I can confirm that inside my transaction log. Yep, looks good. I'm going to look at my requests at 0. Yep, that looks good. Now we're going to do things out of order here a little bit. Notice that we have an approval count of 0 right now. So if I try to finalize this request at this point, I should definitely see an error message. So I'll enter in finalize request of 0 and click on finalize. And actually, before I do that, I'm going to clear out my log here just so I can see everything that happens very clearly. All right, so correctly, we definitely see an error message, which is exactly what we want. Next, I will attempt to approve the request, and I want to approve the request at index 0. Okay, that looks good. And now, when I attempt to finalize request again, I should see success, and I should also see that the second account in that listing up top has slightly more Ether than it had before. So I'll click finalize request. Everything looks good over here now. And if I go back up to the drop-down, I see that the second account has received some additional amount of Ether. Cool. So I think the contract is behaving the way we expect. There is one last quick thing I just realized. Let's try finalizing that request one more time. So if I click on finalize request again, perfect. We see a nice error message because that thing has already been marked as processed or completed. I think that our contract is now at a really good spot. So let's continue in the next video, and we're going to start taking this contract and putting together some tests for it and writing up the front end application. So quick break, and I'll see you in just a minute. We've now got our contract in a pretty good spot, and I think we've written just about all the functions that it needs at this point. So it's now time for us to start pivoting and putting some attention into the front end of our application. I haven't really said a whole lot about the front end that we're going to build, so I want to now give you a little bit more information about it. I want to build a front end to our application that is very similar, or at least somewhat similar, to Kickstarter, in especially one regard. Particularly, I want to make sure that the front end application that you and I build has support for multiple different campaigns. If I go over to Kickstarter.com right now and get a listing of all the different active projects, you'll see that there are currently 36,000 projects. All this time, you and I have been writing code to model one individual project or one single campaign. So it seems to me like we need to put a little bit of thought on how we're going to take this one single campaign and somehow replicate it up to 36,000 times inside the application that you and I are going to make. So in this video, we're going to talk about some of the different approaches and methodologies that we can use to handle deploying this one singular contract right here multiple times. Before we start that discussion, there's one quick thing that I want to remind you about deploying a contract. Whenever we deploy a contract, we are deploying an instance of it to the network. In this case, maybe the Rinkeby blockchain or the Rinkeby network. For every single instance of a contract that you and I deploy, we get back one very unique address. So here's an address here. If we deploy another instance, maybe we get a totally different address over here, a different address over here, and a totally different address over here. The thing to keep in mind here is that each of these addresses are completely divorced and separate from each other. In other words, if we deploy two instances of the campaign contract, there is absolutely no linkage, no connection between them whatsoever. So if I want to show my users a list of these 4 campaigns, that means that after deploying each of these contracts, I need to write down this address, I need to record it, and then anytime I want to show people information about these contracts, I need to go and retrieve information from each of these respective addresses. So that definitely sounds like quite the undertaking, right? It sounds like that's quite a bit of work. Well, I'm going to show you in this video a couple of different ways that we can approach this problem. So let's get to it. All right, so here is a very quick mock-up of what our application might eventually look like. Our application is going to look way better than this, don't worry, but at least this will give you some rough idea of what we're thinking about. Whenever a user comes to our product, I want them to see a listing of all the different campaigns. And like we just said, each of these campaigns will be coming from a very different address. So it seems to me like that deployment process, like the process of creating a new instance of our contract, is something that we want to have a very good understanding of. Like you and I want to really know what happens and how we're going to deploy these new campaigns, because every time we do a campaign, we have to record the resulting address. Otherwise, how are we going to get the information on the screen? We have to have the address to show details about all of our campaigns inside of our product. So again, I think it all really comes down to how we deploy our contracts. Specifically, I think it comes down to the functionality of this Create Campaign button. So we're going to look at a couple of different diagrams that show you 3 possible things that could happen, or 3 possible paths that we could take of handling a user clicking on this Create Campaign button. So let's look at these 3 different ways, and we'll talk about the pros and cons of each one. All right, so let's imagine that a user clicks on that Create Campaign button, and we want to do 2 things when the user clicks that button. First off, we want to deploy a new instance of our contract, and we want to make sure that we get that address so that we can show that new campaign on the screen to all of our other users after it has been created. So in other words, if we deploy campaign C, I want to get the address from a user deploying that new campaign and show it on the screen to everyone else. So here's solution number one that we could take. We could say that a user clicks on the Create Campaign button, and then maybe we take our contract source code and we send it down to the user's browser. Then inside the user's browser, we could use a combination of Web3 and MetaMask to deploy a new instance of our contract. When the user deploys this contract from their browser, they will get back an address, right? That's what happens when you do the deployment. You get back an address. So after the user deploys the contract, they take that address and they send it back to us. So they send it like maybe back to our server or something that you and I control. We then take that address and we publish it very publicly on our site as a brand new campaign. So maybe during this entire process, the user just created campaign C. When we get the address for campaign C, we then add it to the listings of all the different campaigns that we are currently managing on our platform. So this is solution number one right here. This is one possible way of resolving the problem of kind of handling all these different addresses floating around. Solution number one, however, has one gigantic issue, one big security hole in it. Probably others, but I'm going to show you one particularly very large one. Let's imagine that we have a very malicious user, and maybe this is a very clever malicious user. So maybe when this user clicks on Create Campaign, we send the user our contract source code, but then maybe just before deploying the contract, maybe our user modifies the contract source code in some fashion. For example, maybe they remove the entire approvals system or the entire requests system. So maybe anytime someone sends some money into their brand new campaign C, it automatically gets funneled directly back to that user, back to this malicious user right here. Anytime we send our user the contract source code and then have them deploy it, we are essentially putting our fate in their hands. They could make changes to that contract, deploy it, and then send us the resulting address. And it would be rather challenging for you and I to figure out whether or not the user had done something malicious during the deployment process. Remember, our platform that we are putting together here, our product, we want to make sure that users have some reasonable ability to trust all the campaigns that have been deployed on our campaign. If it turns out that like half of our campaigns are malicious and will just hijack the user's money, well, no one's going to use our platform. No one's going to create a campaign with us because as far as they know, they're going to be sending their money into nothingness and just instantly get scammed. So it sure seems to me that we do not want to allow our users to ever get a hold of our contract source code. Or maybe a better way of putting it would be to say we don't want to trust our users in having deployed a correct version of our contract. So that's solution number one, and that's just one very easy to point out problem with this solution. Let's now move on to solution number two. So this is one different way of approaching this. So this kind of takes us to the entire opposite end of the spectrum. With solution number one, we said that the user handling the deployment was a big security hole. So maybe with solution number two, we say that whenever a user clicks on this button, Create Campaign, maybe our server or like your account, my account will be used to deploy a brand new campaign. And then we immediately take that address and you and I are 100% confident that we have just deployed a valid contract to the network. We can take that address and we can very confidently display it inside of our application as like say a brand new campaign C over here. So what's the issue with this approach? Well, remember, any single time we create an instance of a contract or any time we deploy a contract, it costs some amount of money. Deployments of contracts are not free, it costs money. So in this solution number two right here, yeah, we get dramatically increased security. However, we also are going to pay for it severely. If a user comes along and clicks on this Create Campaign button like 500 times, well, are we going to get billed for 500 creations of a contract? I sure hope not. Yeah, I definitely hope that's not the case. So it definitely seems like we do not really want to take the burden of paying for the deployment on ourselves. So it kind of seems to me like we need some intermediary or some kind of hybrid approach between solution number 1 and solution number 2. Let's take a pause right now. We're going to come back in the next video and we're going to talk about this hybrid solution that we're going to use for deploying our campaigns. In the last video, we spoke about 2 different ways of handling deployments of our campaigns. Solution number 1 put all the power of deployment onto our users. The issue with solution number 1 was that it introduced a big security hole, which was definitely not ideal. Solution number 2 solved that security hole by putting the burden of deployment on us, the people who are deploying the server and the overall application. The downside to solution number 2 was that it made you and I responsible for the cost of deploying campaigns, and we definitely don't want to have to pay for that. In this video, we're going to talk about a third possible solution. This is going to be a sort of hybrid approach that takes the best qualities of solution number 1 and solution number 2 and combines them together. All right, so let's take a look at this. So this time around, before we ever release our application into the wild where people can make use of it, you and I are going to deploy a second contract. So we're going to write a second contract and we're going to deploy it before we ever release our application out to the wild. This second contract that you and I are going to make is going to be a manager of sorts. It's going to manage all the different instances of campaigns that eventually get deployed to the Rinkeby network or whatever network we're making use of. We're going to refer to this second contract as a factory of sorts. The purpose of this factory is to create new instances of our campaign. Now that's a little bit tough to wrap your head around. And before you ask the question, I'm going to answer the question that you very likely have. Can a contract deploy another contract? The answer is yes. We can take one contract and have it deploy another. So inside of our Remix editor over here, we have one contract right here. We are going to create a second contract inside of the same file. And this second contract will have one purpose. And that purpose is to create and deploy instances of the campaign. So we're going to write that contract and deploy it. Then at some time in the future, after we actually release our product to the outside world, if a user clicks on the Create Campaign button right here, we are going to tell that user's copy of Web3 and MetaMask to send a transaction to this campaign factory that you and I are going to put together. Whenever one contract deploys another, the cost of deployment is on the user who sends the transaction. So in solution number 3 right here, the deployment is being handled by our new factory contract, yes, but the actual payment for that is going to be on the user. So like I said, this is a type of hybrid approach where you and I are in much greater control of the code that is getting deployed. However, it is still the user who has to pay for the deployment. So the user is going to pay for that cost, and then our factory will deploy a new copy of the campaign. The campaign factory will also be used to store a list of all the different campaigns that have been deployed. So this is where we can have one central location that gives us a canonical list of addresses of all the deployed campaigns. This is a really great solution right here because not only is the campaign factory going to be in charge of deployments, but it also manages all the different instances that are out there. And when I say manage, well, it doesn't have a lot of control, but at least keeps a record of what instances of campaign have been deployed. Now this flow diagram right here is kind of not the best way of showing what's going on. So I want to talk about solution number 3 one more time. We're going to kind of do it again from start to finish, but this time we're going to look at a diagram that's going to make it a lot easier to understand what's going on. All right, so on the right hand side here, we have our Rinkeby blockchain or our Rinkeby network. So you and I are going to write this campaign factory contract, and we are going to deploy it ourselves to the Rinkeby network or to whatever network we want to deploy it to. This is going to be a one-time deployment because we're going to have one factory that is going to be in charge of all of our different campaigns. The factory contract itself is going to contain all of the source code for an individual campaign. And so when I say all the source code for an individual campaign, I'm talking about this campaign contract right here. So the factory has a canonical, clean, unspoiled version of the campaign source code. So there's absolutely no chance of someone getting in here and rewriting the contract or modifying it in any way, shape, or form. Then at some point in time in the future, a user might want to create a new campaign. That user is going to send a transaction to the factory, and that transaction is going to include some amount of money to pay for the deployment. Remember, there's the gas cost in there. The factory will take that money, it will create a new instance of a campaign using the stored campaign source code that it has right here, and then it will deploy a new campaign to the Rinkeby blockchain. And remember, when it gets deployed, it will be deployed with some brand new address. The factory will then take that address, record it, and store it within the factory contract itself. So the factory always has a list of all the different campaigns that have been deployed. That means that at some point in the future, when our product, when our Kickstarter platform wants to get a list of all the different campaigns that have ever been created, we can issue a simple query to the factory, and the factory will return a list of all the different addresses that it contains. Okay, so that's a simple walkthrough of what's going to go on here. I feel like the biggest challenge here to understand is simply the fact that we can write one contract that deploys another contract. And the other thing that's probably a little bit challenging to understand is the fact that these addresses are really important to keep in some location, because eventually we're going to want to get a list of all the deployed campaigns. And so because the factory stores that list, we're always going to have one sacred location that says, hey, here's a list of all the campaigns that have ever been deployed. Now that we've got a better idea of how we're going to solve all this deployment stuff, let's continue in the next video where we're going to start working on this factory contract. So I'll see you in just a minute. In the last video, we spoke about how we would solve the issue of deployment inside of our application. We're now going to start working on our factory contract that will handle the deployment and record of all the deployed instances of campaigns. Before we start writing any code, I'm going to give you a quick outline of the design of this campaign factory. So we're going to call it campaign factory. We could just as easily call it factory, whatever you want to call it, either one is appropriate. This contract is going to have one variable. It's going to be an array of addresses that contains all of the deployed campaigns that have ever been created. The campaign factory will also have two functions. First, it will have a create campaign function. And as you might guess, this is going to deploy a new instance of an individual campaign and then store the resulting address back inside of the deployed campaigns array. We also need to make sure that we have the ability to get that big list of campaigns back to our application. And for that, we're going to make another function called getDeployedCampaigns. And essentially, all this does is return all the data inside of deployed campaigns. Remember, whenever we make an array with Solidity, the built-in getter that is provided to us for an array only retrieves one element. And we don't want to retrieve all the deployed campaigns one campaign at a time. Instead, we want to be able to retrieve all of them instantly in one function call. So that's why we're going to make this separate function right here. All right, so let's flip over to Remix and start working on this contract. The code for this is actually going to be very, very straightforward. It's really just understanding what's going on that's the real challenge here. So back inside of Remix, I'm going to create a new contract right above our existing one. So I'm going to give myself a little bit of space, and then I'll say contract campaign factory. Inside of here, we'll declare that new variable to hold the list of all of our different deployed campaigns. So address, public, deployed campaigns. Next, we'll declare the function that allows a user to create a new instance of a campaign. So this will be our create campaign function. This function is going to need to take one argument. Remember that right now, we are expecting that whenever someone creates a campaign, they provide a constructor argument of the minimum amount of money that needs to be donated. So because the constructor requires this argument right here, and we are no longer going to expect any users or anyone at all to directly be creating a campaign, we have to make sure that the create campaign function right here receives that argument, that minimum contribution argument, and passes it along to the new campaign constructor function. So as an argument to this thing right here, we'll take in a uint called minimum. So this is the minimum contribution that our new campaign expects. Now here's where the magic happens. Right inside this function, we are going to instruct this contract to deploy a new instance of campaign. To do so, we write out new campaign and then provide any constructor arguments that this thing requires. And in this case, the only thing it requires is the minimum contribution. So we can pass in minimum like so. So that's pretty much it. This right here creates a new contract that gets deployed to the blockchain. After that deployment occurs, it then returns the address of the newly created campaign. So we can store that newly created address in a local variable and then add it into the deployed campaigns array. So we can say that we're going to create a new variable of type address. We'll call it new campaign, and its value will come from the campaign creation line right here. Then immediately after that, we can take this new address or this new campaign and add it to the deployed campaigns array. So deployed campaigns dot push new campaign like so. Cool. So that's pretty much it. Now there's one thing that is a little gotcha here around this deployment process. This is a little bit of a gotcha. Back down inside of our campaign constructor function, you'll recall that we not only are expecting to get this argument of minimum passed in the constructor, but you'll recall that we also use the constructor to set up the manager of our contract. So unfortunately, whenever we create a new contract or whenever we call this constructor function from another contract, the message.sender will be the other contract, not our user. So if we currently use the factory to create a new instance of campaign, the manager will be marked as our factory's address. And the manager is definitely not our factory. The manager is whoever had originally asked for this new instance of campaign to be created. In order to get access to the address of the person who is trying to actually create the new campaign, we're going to need to get that address from inside of the create campaign function right here, and then pass it into the constructor of the campaign argument right here. Or excuse me, the constructor of the campaign contract, my mistake. Again, this is all because whenever we have one contract build another, the message variable, the message global variable inside campaign will be the campaign factory, not the user who's trying to make this thing. So in short, that's just a long description for saying we have to pass in message.sender right here. So at this function, at create campaign, message.sender is the user who is trying to create the new campaign. So this is definitely the correct address right here. So now we can go down into the campaign. We can receive that address as an argument. So we'll say address, and we can call this, I don't know, let's just call it creator to make sure that it's really obvious what it is. So creator right here is the address of the person who is actually trying to create the new contract. And then rather than using message.sender, which is the address of the factory, we will use the creator address, like so. Okay, so that's pretty much it for create campaign. Now the last thing we have to do is to make sure we add a function that returns the entire array of deployed campaigns. And that's going to be pretty quick, so let's just do it right now. Inside of here, we'll add on function get deployed campaigns. This takes no argument, but it does return an array of addresses. So we can say public view returns address array, like so. Remember that public means that anyone can call this function. View means that no data inside the contract is modified by this function. And then returns address array obviously means that we are going to return a value of type address array. Then inside of here, we can add on return deployed campaigns. So there's our factory in total. We now have one function to create a new campaign, and then we have another function to return a list of all the campaigns that have been created. Let's take a pause here. We'll come back in the next video and we'll test this thing out by using Remix. So I'll see you in just a minute. In the last video, we created our campaign factory contract. We're now going to use Remix to test this thing out and make sure that it's working the way we expect. So remember, from now on, we're not going to be creating campaigns directly ourselves. Instead, we're going to create a campaign factory and then ask this thing to create campaigns for us. I'm going to open up the right-hand nav. I'll select Run. I'll make sure that I delete any existing contracts I've already got in here. I'll make sure that I've got JavaScript VM selected. I'm going to select the top account. And then I'm going to select in this drop-down right here, Campaign Factory. So no longer do we want to create an instance of Campaign, we want to make Campaign Factory. I'll create Campaign Factory. So here's our instance of Campaign Factory right here. Again, I can't say it enough. Remember, we're only ever going to be working with one copy of this thing. Now we can use this to create a new instance of a campaign. It takes a single argument whenever we create a campaign, and that is the minimum contribution to the campaign. So again, I'm going to use 0 right here because I don't really care about any minimum contribution or anything like that. So now I can click on Create Campaign, and before I do, I'm going to pull up my terminal right here. So here's Create Campaign. That creates a new instance of campaign for us. If we now click on the Get Deployed Campaigns button, we'll see the address of the campaign that was just created. So now we want to somehow manipulate or make use of the contract that exists at this address right here. Eventually, as we start to work on our front-end application, we'll take this address and use Web3 to interact with it. But I do want to show you how you can interact with this contract by using Remix as well. If you highlight this address right here and copy it, you can then come back up to this little Create Contract selector right here. You can change the drop down back to Campaign, and then rather than clicking on Create right here, we can enter in that address to the @address input right here. So Remix allows you not only to create new contracts on the fly, but you can also have it kind of interact with already deployed contracts as well. So I can paste in that address, click @address, and then I'll see the campaign that we just created appear right here. So this is the campaign that was just created by our campaign factory. And we can interact with it just as we normally would. So for example, I could print out the manager. Here's my address right here. You'll notice that it is correctly using my address rather than the campaign factory address. We could get, say, approvers count 0 because no one's donated to it just yet. And hey, I'm sure everything else inside of here works just as well. All right, so that's pretty much it. That is a demonstration of our campaign factory in progress. Again, we are using this idea of a factory not only to add some level of security to our deployments, but also give us the ability to easily keep track of all the existing campaigns that have ever been deployed inside of our application. I think that's pretty much it for what we have to do inside of Remix for right now. So let's continue in the next section, and we're going to start writing our actual tests for these contracts. So I'll see you in just a minute.